The Earth is a marble, a glass marble, blue and white, swirled with the colours of ocean and cloud, small enough to sit in the palm of your hand. You have seen this marble before. Perhaps you held one as a child, rolling it between your fingers, watching the light catch its surface. The Earth, compressed to this size, would measure approximately 1 inch across, 25 millimetres, the width of a quarter. You could lose it in your pocket, mistake it for loose change, drop it between the cushions of your couch and never find it again. This is not metaphor. This is scale, and what follows will shatter every intuition you possess about the distances that separate you from everything beyond the thin blue atmosphere of your home. Because when we shrink our planet to something we can hold, when we make it physical and familiar and small, the true architecture of the solar system reveals itself as something so vast, so empty, so impossibly stretched across space that the mind recoils from comprehension. If you find yourself curious about the true scale of our cosmic neighbourhood, and if you enjoy content that makes you see the universe differently, please consider liking and subscribing. It truly helps more than you know. Now hold that marble in your mind, feel its weight, because we are about to walk outward from everything you know, step by step, into distances that will transform how you understand your place in existence. Are you ready? Let us begin. The marble sits in your hand, 1 inch, 25 millimetres. At this scale, Mount Everest, the highest point on Earth, the peak that has claimed hundreds of lives and demanded the absolute limits of human endurance to summit, would be a bump so small you could not feel it with your fingertip. The Mariana Trench, plunging nearly 7 miles below sea level into crushing darkness, would be an invisible scratch on the surface, a flaw in the glass so fine that no human eye could detect it. The atmosphere itself, that thin envelope of gas that separates life from the void, that contains every breath ever drawn by every creature that has ever lived, would be a layer of varnish thinner than a coat of nail polish. If you breathed on the marble and it fogged, that fog would extend further from the surface than our atmosphere does at this scale. The boundary between Earth and space, the line we call the Kármán line at 100 kilometres altitude, would sit less than 0.2 of a millimetre above the glass surface. A single sheet of paper is thicker. The difference between the breathable air that sustains 7 billion humans and the lethal vacuum of space is, at this scale, essentially nothing. This is the first lesson of the model. Even the features that seem vast to us, even the distances that define the limits of human experience on Earth, compress to near invisibility when we shrink our planet to the size of a marble. And we have not yet begun to travel outward. The moon comes first, Earth's constant companion, the silver disk that has governed tides and calendars and mythology since before humanity existed, the only world beyond our own that human beings have ever walked upon. 12 men have left footprints in its dust. 24 have seen the Earth rise above its horizon. The moon is not close. The moon is not just above us, floating in the sky like a lantern hung for our convenience. At true scale, compressed alongside our marble Earth, the moon would be a ball bearing approximately 1/4 inch in diameter, about 6.5 millimetres, roughly the size of a peppercorn or a small bead. And where would this peppercorn sit relative to our marble? 30 inches away, 2.5 feet. Hold your marble Earth in one hand, extend your arm fully to the side, and the moon would hover somewhere near your opposite shoulder. This is the closest any natural object comes to our world. This is the full extent of human physical exploration beyond the atmosphere. In 60 years of spaceflight, of rockets and capsules and heroic missions, of billions of dollars and thousands of engineers and the combined will of nations, we have travelled 30 inches. Picture this distance. Stand in the centre of a room, hold your marble. The moon peppercorn floats 2.5 feet from your outstretched hand. You could take a single step and close the gap. You could reach across a small table. The Apollo astronauts, travelling in spacecraft no larger than a compact car, their lives sustained by systems that would fit in a modern bathroom, crossed this gap in 3 days. They coasted through the void for 72 hours, watching the marble Earth shrink behind them and the peppercorn moon grow ahead, traversing what is, at this scale, the length of your arm. And yet this distance, this seemingly reachable span, contains emptiness beyond human experience. At true scale, the 250,000 miles between Earth and Moon could fit 30 Earths placed side by side in a perfect line. The gap is not a void full of blackness. It is a void full of nothing. No air, no sound, no medium of any kind. If you screamed at the exact centre point between Earth and Moon, the sound waves would propagate approximately 0 inches before dying, having no molecules to carry them forward. The astronauts of Apollo travelled through absolute silence, through a vacuum so perfect that it would pull the air from their lungs in 14 seconds if their suits failed, through a darkness broken only by the unfiltered glare of the sun and the cold glow of distant stars. 30 inches, 2.5 feet, and most of humanity will live and die without ever crossing it. But the Moon is merely the foyer, the entrance hall, the coat closet of the solar system. To understand the true architecture of our cosmic neighbourhood, we must continue walking outward, and here is where the distances begin to strain credibility. Mars, the red planet, the target of humanity's next great adventure, the world that has captured human imagination since ancient astronomers first noted its rusty, wandering through the constellations. Mars at opposition, at its closest possible approach to Earth, would be located, in our model, approximately 300 feet away from your marble. 300 feet, the length of a football field. If you stood on the goal line holding your inch-wide Earth, Mars would be a ball roughly half an inch across sitting on the opposite end zone. But Mars is rarely at opposition. For most of its orbit, Mars ranges much farther from Earth, sometimes as distant as 250 million miles, when both planets sit on opposite sides of the Sun. At maximum separation, in our model, the half-inch Mars would be positioned over 2,000 feet from your marble Earth. That is nearly half a mile. You would need binoculars to see it. You would need to leave the football stadium, walk several blocks and find a distant rooftop before the red speck became visible against the background. Consider what this means for human exploration. Every mission to Mars, every rover that has rolled across Martian soil, every orbiter that has photographed the planet's ancient river valleys and towering volcanoes, required crossing this gap. At the speed of the Parker Solar Probe, humanity's fastest object, the journey to Mars at closest approach would still require over 100 hours of continuous flight, but spacecraft to Mars do not travel in straight lines. They arc outward in curved trajectories dictated by orbital mechanics, trading speed for efficiency, falling around the Sun in paths that add months to the journey. The Perseverance rover, launched in July 2020, arrived at Mars in February 2021. 7 months of travel. 7 months of hurtling through vacuum at speeds exceeding 15,000 miles per hour. 7 months to cross 300 feet at marble scale. The emptiness between those 300 feet is absolute. There are no rest stops, no refueling stations, no opportunities to turn around if something fails. The spacecraft that make this journey carry everything they will ever need. Their solar panels unfold to catch light from a sun that grows dimmer with each passing day. Their communication systems reach back toward an Earth that shrinks to a blue point, then to an indistinguishable speck, then to a memory of a speck among thousands of other specks. The delay in communication stretches from seconds to minutes. By the time a mission controller on Earth sends a command, the signal has travelled for 3 to 22 minutes depending on planetary positions. By the time the response returns, nearly an hour may have passed. Conversations become impossible. Every instruction must anticipate every possible failure. Every robot on Mars operates for all practical purposes alone. And Mars is close. Mars is a neighbour. Mars is the first step onto the porch of a house that extends further than you have yet imagined. Before we walk further outward, we must establish the centre of our model. The Sun, the nuclear furnace that accounts for 99.86% of all mass in the solar system. The engine of light and heat and gravity that holds 8 planets and billions of smaller objects in its grip. In our scale model, with Earth as a 1-inch marble, the Sun would be a sphere approximately 9 feet in diameter. 9 feet. The height of a basketball hoop. The width of a large bedroom. A ball so large that you could not wrap your arms around it, could not reach across it, could not stand beside it without feeling dwarfed. And where would this 9-foot Sun sit relative to your marble Earth? 400 feet away, 120 metres, the length of 4 Olympic swimming pools placed end to end. If you held your marble in the centre of a football field, the 9-foot Sun would sit somewhere in the parking lot. At this distance, in our model, the Sun would appear as a bright disk about 1 inch across when viewed from your marble, which matches exactly the apparent size of the Sun as seen from Earth's surface. The mathematics are consistent. The model holds. But consider what this distance means. Light, the fastest thing in the universe, the absolute speed limit of existence, travels at 186,000 miles per second. Light leaving the surface of the Sun requires 8 minutes and 20 seconds to reach Earth. In our marble model, this means light crosses those 400 feet in slightly more than 3/10 of a second. Light is fast. Light is unimaginably, incomprehensibly fast. And yet even light requires 8 minutes to bridge the gap between the parking lot and the centre of the field. The sunlight warming your skin at this moment left the solar surface when you were doing something else. If the Sun vanished right now, winking out of existence in an instant, you would continue to see it shining for another 8 minutes and 20 seconds. You would feel its warmth, see its light, have no indication whatsoever that the heart of the solar system had stopped beating. And then the sky would go dark, and 8 minutes later, Earth would begin to drift away from where the Sun had been, no longer held in orbit, beginning a long, slow journey into the interstellar void. The 9-foot Sun, 400 feet from your marble, contains almost everything. The planets are rounding errors. Jupiter, the largest, would be a ball roughly 1 inch in diameter, about the same size as Earth in our model, but with 63 times the volume when properly scaled, and it would orbit 2,000 feet from the Sun. 5 times further than Earth, a third of a mile, Saturn, with its rings, would be a ball slightly smaller than Jupiter, orbiting nearly 4,000 feet out. 3/4 of a mile. You could not see Saturn from the Sun with the naked eye at this scale. It would be a speck, a mote, a dust particle hanging in darkness at the edge of visibility. The outer giants push further still. Uranus orbits at approximately 8,000 feet in our model, 1.5 miles from the centre of the solar system. Neptune, the wind-swept ice giant, sits at roughly 13,000 feet, 2.5 miles from your marble-sized Earth, 2.5 miles from the 9-foot Sun. If you stood in the centre of a city holding your marble, Neptune would be somewhere in the suburbs, beyond the downtown, beyond the neighbourhoods, out where the streetlights grow sparse and the buildings give way to empty lots. And Pluto, the dwarf planet at the edge of the classical solar system, the frozen world that remained undiscovered until 1930, orbits at an average distance of 17,000 feet from our model Sun, 3.25 miles. You could spend an hour walking from the 9-foot Sun to the peppercorn-sized Pluto. You could drive there in 5 minutes, but at true scale, light from the Sun requires 5.5 hours to reach Pluto. A spacecraft travelling at 40,000 miles per hour would require nearly a decade. The New Horizons mission, launched in January 2006 to become the first spacecraft to visit Pluto, did not arrive until July 2015. 9.5 years of travel. 9.5 years of patient coasting through the void, past Jupiter, past Saturn's orbit, past Uranus, past Neptune, into a realm of the solar system where the Sun has shrunk to a bright star among stars and temperatures hover near absolute zero. 9.5 years to cover 3.25 miles at marble scale. And when New Horizons finally reached Pluto, it screamed past at 36,000 miles per hour, capturing images during a flyby that lasted hours before continuing outward into the Kuiper Belt. Too fast to stop, too committed to turn around, trading intimacy for the simple achievement of arrival. The solar system at this scale fits within a comfortable walk, 3.25 miles from Sun to Pluto. You could map it on a city sidewalk. You could trace it through a suburban neighbourhood. You could walk from Mercury to Neptune in an afternoon, pausing at each planet to place a marble or a ball bearing or a grain of sand depending on their relative sizes. Mercury, the innermost planet, would be a grain of salt roughly 1/10 of an inch across, orbiting 160 feet from the 9-foot Sun. Venus would be a marble slightly smaller than Earth's 1 inch, sitting 300 feet out, Earth at 400 feet, Mars at 600 feet. Then the vast gap to Jupiter at 2,000 feet, Saturn at 4,000 feet, Uranus at 8,000 feet, Neptune at 13,000 feet, Pluto at 17,000 feet. This is the family. This is the neighbourhood. These are the worlds that have occupied human astronomy for millennia. The wandering stars that ancient civilizations named after gods and tracked across the sky with stone instruments and careful mathematics. Every planet in the solar system, from blistering Mercury to frozen Neptune, fits within a circle roughly 6.5 miles across when measured with Earth as a 1-inch marble. But the solar system does not end at Neptune. The solar system does not end at Pluto. The solar system extends far beyond the orbits of the known planets, out into regions where spacecraft have barely reached, and where no telescope can see with any detail. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies and dwarf planets stretching from 30 to 50 astronomical units from the Sun. In our model, the inner edge of the Kuiper Belt begins roughly 3 miles from the 9-foot Sun, and its outer edge extends past 5 miles. The Kuiper Belt contains hundreds of thousands of objects larger than 60 miles across, and billions of smaller fragments. The frozen remnants of the solar system's formation, too distant and too cold to have coalesced into proper planets. Beyond the Kuiper Belt lies the scattered disk, a region of highly eccentric orbits where ice dwarfs like Eris loop outward into the distant reaches of the Sun's influence. Eris, discovered in 2005 and originally hailed as the 10th planet before the International Astronomical Union reclassified Pluto and created the dwarf planet category, orbits at an average distance of 68 astronomical units from the Sun. In our model, this places Eris roughly 6.5 miles from the 9-foot Sun. 6.5 miles, over an hour of walking, nearly 3 hours of walking from your marble Earth. And beyond the scattered disk lies the Oort cloud. The Oort cloud exists at the edge of theoretical. No spacecraft has visited it. No telescope has directly imaged it. We know it exists because long-period comets occasionally fall from its depths, plunging toward the inner solar system on trajectories that take millions of years to complete, trailing tails of sublimating ice as they briefly warm before returning to the frozen dark. The Oort cloud is a spherical shell of icy bodies surrounding the entire solar system, a reservoir of primordial material left over from the Sun's formation 4.5 billion years ago. Its inner edge begins at approximately 2,000 astronomical units from the Sun. Its outer edge extends to perhaps 200,000 astronomical units. In our marble scale model, the inner Oort cloud begins roughly 190 miles from the 9-foot Sun. 190 miles. The distance from New York City to Washington, D.C., the distance from Los Angeles to Las Vegas. You could not walk there in a day. You could not walk there in a week. At a steady pace of 3 miles per hour, walking 8 hours daily. Reaching the inner edge of the Oort cloud from your marble Earth would require over 8 days of continuous hiking. And the outer edge of the Oort cloud, the true boundary of the Sun's gravitational influence, the point beyond which objects would drift away into interstellar space, sits approximately 19,000 miles from our model Sun in the marble scale. 19,000 miles, the circumference of the Earth. You could circle the entire planet walking west from New York and returning from the east, and you would have travelled the same distance as the span from the 9-foot Sun to the outer edge of its gravitational domain. This is the solar system. This is the full extent of our star's kingdom. A 9-foot ball casting its influence across a sphere 19,000 miles wide, holding trillions of objects in its gravitational grip, from the 8-minute march of light to Earth, to the 6-month journey to Mars, to the 9-year odyssey to Pluto, to the theoretical voyages of thousands of years to the outer cometary halo. And at the centre of this inconceivable expanse, sitting 400 feet from the 9-foot Sun, lies your 1-inch marble, blue, white, swirled with cloud and ocean, home to every human being who has ever lived or ever will live within the foreseeable future. The solar system is vast. The solar system is empty beyond comprehension. The gaps between planets contain nothing but vacuum and radiation and the occasional wandering asteroid or comet nucleus. If you shrunk yourself to the size of a dust mote and floated between Earth and Mars, you would likely drift for years without encountering any object larger than a grain of pollen. The solar system is not a crowded neighbourhood. It is a desert larger than continents, larger than worlds, scattered with occasional outposts of matter separated by gulfs of absolute nothing. And yet the solar system is not the universe. The solar system is not the galaxy. The solar system is a single house, on a single street, in a single city, in a single country, on a single continent, on a single planet, in a single orbit around a single star. And the nearest neighbouring star, the closest other sun in all the cosmos, lies at a distance that will strain the model to its breaking point and perhaps beyond. Alpha Centauri, the brightest star in the southern constellation of the Centaur. To the naked eye, it appears as a single point of light, the third brightest star in the night sky. Through a telescope, it resolves into a binary system, two sun-like stars orbiting each other at a distance roughly comparable to the gap between our Sun and Uranus. A third component, a dim red dwarf called Proxima Centauri, orbits the binary pair at a vast distance and holds the distinction of being the closest individual star to our solar system. Proxima Centauri lies 4.24 light-years from Earth. Light, travelling at 186,000 miles per second, requires 4.24 years to cross the gap. This is not a metaphor. This is not an approximation. Light that left Proxima Centauri today will not reach your eyes until sometime in the year 2029. The star you see in the sky, if you live far enough south to see it, is not the star as it exists right now. It is the star as it existed during your past, frozen in time, its photons having travelled for years through the void to reach your retina. In our marble scale model, with Earth as a 1-inch marble and the Sun as a 9-foot sphere 400 feet away, how far would Proxima Centauri be? 6,300 miles. This number must be repeated because it does not fit in the human mind on first hearing. 6,300 miles. In a model where the entire solar system from Sun to outer Oort cloud spans 19,000 miles, the nearest star sits at 1/3 of that distance beyond the edge. In a model where Earth orbits 400 feet from the Sun, the nearest star orbits over 6,000 miles away. If you built this model with your marble Earth in New York City and your 9-foot Sun in the parking lot outside your building, where would the nearest star be? The marble-sized Proxima Centauri, a ball perhaps 1/10 of an inch in diameter, representing the small red dwarf, would sit somewhere in the middle of the Pacific Ocean, roughly 1,000 miles west of Hawaii, closer to Japan than to California, separated from your marble by more empty ocean than the entire width of the Atlantic. You could not walk there. You could not drive there. You could not sail there in any reasonable time. The gap between the 9-foot Sun in the parking lot and the tiny red marble floating in the Pacific is a void containing nothing. No planets, no asteroids, no comets beyond the outer Oort cloud, just vacuum, just darkness, just the interstellar medium, a thin scattering of hydrogen atoms averaging roughly 1 per cubic centimetre, less dense than the best laboratory vacuum ever created on Earth. The interstellar medium is not empty in the absolute sense, but it is so close to empty that the distinction collapses for practical purposes. Between our solar system and Proxima Centauri lies a gulf across which no signal has ever been sent with any expectation of reply, across which no spacecraft has ever been designed to travel, across which no human being will journey for centuries or perhaps millennia. The Voyager 1 spacecraft, launched in 1977, travelling at 38,000 miles per hour, the fastest object humanity has ever sent toward the stars, would require over 70,000 years to reach Proxima Centauri if it were aimed in that direction. 70,000 years. Longer than modern humans have existed as a species. Longer than the entire span of recorded history multiplied by a factor of 10. The marble sits in your hand, 1 inch across. The peppercorn moon floats 2.5 feet away. The tennis ball Mars hovers 300 feet distant at closest approach. The 9-foot Sun blazes in the parking lot 400 feet behind you. And somewhere out in the Pacific, 6,000 miles across open water, a speck smaller than a peppercorn marks the nearest other sun. This is the gap. This is the void. This is the truth that the scale model reveals with brutal clarity. The solar system is vast but traversable, at least in theory, at least with technology that extends logically from what we possess today. But the distance to the stars is of a fundamentally different character. It is not merely larger, it is qualitatively other. It is a gap that current technology cannot meaningfully address, that current lifespans cannot meaningfully span, that current physics constrains in ways that make the crossing seem more like magic than engineering. And Proxima Centauri is the closest star, the nearest neighbour, the first step beyond the porch of our solar home. The galaxy contains an estimated 100 to 400 billion stars, scattered across a disk roughly 100,000 light-years in diameter. In our marble model, the Milky Way would extend over 150 million miles in diameter. 150 million miles. The actual distance from Earth to the Sun at true scale. Our entire galaxy, compressed into the marble model, would be a structure so vast that it could contain the real sun sitting at its actual distance from the real Earth. The scale breaks, the model strains, the numbers become meaningless, because they no longer connect to anything the human senses can experience. And yet this is the truth of cosmic distance. This is what lies beyond the blue marble in your hand. This is the context in which Earth exists, in which the solar system drifts, in which our species has evolved and struggled and dreamed. You are holding a marble. Around that marble orbits a peppercorn. Beyond the peppercorn lies a football field of emptiness, before even the nearest planet becomes relevant. Beyond the planets lies a sphere 19,000 miles wide filled with scattered ice and rock, and the fading whisper of the sun's gravity. And beyond that sphere lies an ocean so vast that the nearest shore sits 6,300 miles away, and the far shore cannot be measured in miles at all, but only in years of light travel, in epochs of waiting, in generations of voyaging that would make the journeys of Odysseus look like a walk to the mailbox. This is where we live. This is what surrounds us. This is the architecture of our cosmic address, laid out at a scale you can hold in your hand and walk with your feet, but never quite grasp with your intuition. The distances are too large, the emptiness is too complete, the implications are too profound. And yet we look up, and yet we build telescopes, and yet we launch spacecraft and dream of voyages and plot courses to worlds we will never live to see reached. Something in the human spirit refuses to accept the prison of scale, refuses to bow to the tyranny of distance, refuses to believe that the marble in our hand represents the final boundary of human possibility. The marble sits in your hand, warm from your grip, impossibly small against the darkness that surrounds it. And yet everything you have ever known, everything any human has ever experienced, every triumph and tragedy and quiet afternoon, has occurred on the surface of that marble or in the thin shell of atmosphere clinging to it like morning dew. But we have spoken of distance. We have walked the emptiness between worlds, paced out the void that separates our marble from its neighbours. Now another truth demands attention, a truth that the scale model reveals just as starkly, though it often goes unspoken in the shadow of those enormous distances, the truth of size. Because the marble in your hand is not merely separated from other objects by vast gulfs of emptiness, it is also vanishingly small compared to almost everything else in the cosmic neighbourhood. The distances humble us, but the sizes should terrify us. Return to the parking lot where you placed the sun, 9 feet across, a sphere so large that if you stood at its edge you would need to crane your neck to see the top. Walk around it and the circumference would measure over 28 feet. Stand inside it if you could, and you would be lost in a space that could comfortably hold a small apartment with room to spare for furniture. 9 feet. The sun at marble scale. Now consider what that means. The real sun is 864,000 miles in diameter. Roughly 109 Earths could line up across its face like beads on a string. You could fit 1.3 million Earths inside the sun's volume, not 1 million, 1.3 million. Every human who has ever lived, every city ever built, every ocean ever sailed, every mountain ever climbed, every war ever fought, every poem ever written. All of it has occurred on a marble that could be dropped inside the sun over 1 million times before the sun noticed the crowding. Hold the marble up to your eye. Look at it. Really look at it. That tiny sphere of glass, 1 inch across, light enough to roll across your palm, small enough to lose in a pocket. Now imagine 1.3 million of them. Imagine filling a room with marbles, then a house, then a warehouse. Imagine marbles cascading down in an endless waterfall, piling up in drifts like snow, burying you to your waist, your shoulders, your chin. Imagine drowning in marbles. And when you have imagined all that, understand that you have not yet imagined enough marbles. You would need to fill a space roughly the size of a small stadium to hold 1.3 million inch-wide spheres. The sun, in your hand at model scale, would take up less space than a refrigerator. But it represents a volume that could swallow everything humanity has ever known or will ever know, and still have room for 1 million more humanities besides. The marble is small, we knew this already. But standing next to the 9-foot sun, the smallness takes on a different character. It becomes not merely a fact, but a felt presence, a weight pressing down on your understanding of your place in creation. And the sun itself, vast as it seems in our model, vast as it truly is in space, is not a particularly impressive star. This is where the scale model begins to strain against the limits of what can be meaningfully represented. Because if you wanted to include other stars in your parking lot solar system, you would need to consider not just their distance but their size. And the sizes of stars vary so dramatically that the variation itself becomes a kind of absurdity. Take Sirius, the brightest star in Earth's night sky, blazing in the constellation Canis Major like a diamond sewn onto black velvet. Sirius is roughly twice the mass of our Sun and about 1.7 times its diameter. In the marble model, Sirius would be a sphere roughly 15 feet across. Larger than the 9-foot Sun, certainly, but not incomprehensibly so. You could stand between them, and your mind could hold both objects simultaneously. Both would fit in the parking lot, even if Sirius would dominate the space. But Sirius is merely a bright nearby star. The cosmos contains objects that make Sirius look modest. Consider Betelgeuse, the red supergiant that marks the shoulder of Orion. Betelgeuse pulses with a diameter that varies over time, but at its average size it measures roughly 764 times the diameter of the Sun. 764 suns, laid side by side like oranges at a fruit stand, would stretch across the face of Betelgeuse. In the marble model, where our Sun occupies a 9-foot sphere, Betelgeuse would expand to nearly 6,900 feet across, over a mile in diameter. A sphere so vast that if you placed it in the centre of a major city, it would stretch from downtown to the suburbs, from the financial district to the residential neighbourhoods, from the stadium to the airport. A sphere that would rise higher than the tallest skyscrapers ever constructed, that would blot out the sky, that would transform the marble earth into something so small it would be invisible to the naked eye even if you knew exactly where to look. And Betelgeuse is not the largest star. The supergiant UY Scuti, located in the constellation Scutum roughly 9,500 light-years from Earth, holds a contested claim as one of the largest known stars. Its diameter measures approximately 1,700 times that of the Sun, 1,700 suns across. In the marble model, UY Scuti would expand to over 15,000 feet in diameter, nearly 3 miles, a sphere that would swallow entire city centres, that would stretch from one end of Manhattan to the other, that would contain within its volume not just skyscrapers but entire neighbourhoods, parks, rivers, the accumulated infrastructure of centuries of human construction. All of it would fit inside the model-scale representation of a single star that exists somewhere in the distant reaches of the Milky Way, 3 miles across, for a single star, in a model where Earth is a 1-inch marble. The scale breaks again. The model strains again. The numbers detach from experience again. But this is the reality. This is what exists. This is what hangs in the void alongside our tiny marble, separated by distances so vast they numb the mind, and possessing sizes so enormous they make the distances seem almost intimate by comparison. Hold the marble to your eye one more time. Look at its surface. Imagine the continents painted there, the ocean swirling blue, the ice caps gleaming white at the poles. Now imagine that marble dropped into a hollow sphere 3 miles wide. Imagine it falling and falling and falling through empty space within that sphere, lost in the darkness, too small to find, too insignificant to matter. That is what Earth would look like inside some of the stars that burn in our galaxy. That is the proportion. That is the relationship between our world and the cosmic furnaces that light the universe. And the stars themselves, enormous as they are, gather into structures larger still. The Sun sits within the Milky Way galaxy, one star among an estimated 200 to 400 billion. That number is so large that it resists intuition entirely. If you counted 1 star per second, 24 hours a day, never sleeping, never pausing, never faltering, it would take you somewhere between 6,000 and 12,000 years to count them all. Longer than recorded human history. Longer than the span from the construction of the pyramids to the present day. And you would be counting not objects you could see, not things you could touch, but points of light so distant that the light reaching your eyes left those stars before your parents were born, before your grandparents were born, before entire civilizations rose and fell on the marble in your hand. In the marble model, we established that the Milky Way would stretch 150 million miles across. The distance from the real Earth to the real Sun, our entire galaxy, compressed to marble scale, would span the gap that our planet actually travels in its orbit. The model and the reality converge at a single point of absurd coincidence, as if the universe were playing a mathematical joke whose punchline we are only beginning to grasp. But consider what this means in terms of size rather than distance. Consider what it would mean to construct a marble-scale model of the Milky Way. You would need hundreds of billions of objects ranging from tennis ball Earths to 3-mile supergiant spheres. You would need to scatter them across a volume 150 million miles in diameter, but only a few million miles thick. A disc-shaped structure spinning slowly in space. You would need to fill the centre with a dense bulge of older stars, crowded together like rush-hour commuters, while the spiral arms extended outward in graceful curves, decorated with bright young stars and glowing nebulae and dark lanes of dust. You would need, at the very centre, a black hole, a region where space itself curves so dramatically that nothing, not even light, can escape. The black hole at the centre of the Milky Way, called Sagittarius SSO, contains the mass of roughly 4 million suns compressed into a region smaller than the orbit of Mercury. In the marble model, this black hole would occupy a space roughly 50 feet across, a sphere of pure absence sitting at the heart of the galaxy, like a dark jewel in a crown of fire. The image staggers. The model collapses under its own weight. No parking lot, no city, no country could contain such a construction. The marble model works for the solar system, because the solar system, vast as it is, remains bounded, comprehensible, a structure you can walk across in a day if you accept a few liberties with the placement of Pluto and the Kuiper belt. But the galaxy defies such treatment. The galaxy is too large, too complex, too filled with objects at too many different scales to fit into any model that human feet could traverse, and the Milky Way is merely one galaxy. Return to the marble in your hand. Feel its weight. Feel its smooth surface, the slight warmth where your fingers have pressed against the glass. This tiny sphere, 1 inch across, represents everything you know. And beyond the 9-foot sun, beyond the model-scale Proxima Centauri sitting in the Pacific, beyond the 150 million mile disk of the marble-scale Milky Way, lies the rest of the universe. The Andromeda Galaxy, our nearest large galactic neighbour, sits roughly 2.5 million light-years from Earth. In the marble model, where 1 inch equals roughly 8,000 miles of actual distance, Andromeda would float approximately 2.5 billion miles away, beyond the orbit of Neptune, beyond the Kuiper belt, out in the realm where the solar system's furniture becomes thin and sparse, where even Voyager 1 has not yet ventured at its position 19 billion miles from home. In the marble model, the nearest major galaxy would sit so far from your parking lot sun that the light of that sun would be invisible, a speck below the threshold of human vision, lost in the dark. And Andromeda is the close one. The observable universe extends roughly 46 billion light-years in every direction from Earth. The cosmic horizon, the boundary beyond which light has not had time to reach us since the Big Bang, defines a sphere roughly 93 billion light-years in diameter. 93 billion light-years. In the marble model, this sphere would expand to approximately 9.3 trillion miles across. 9 trillion miles. A number that has no referent in human experience, that cannot be walked or driven or flown, that can only be stated and then left to sit in the mind like a stone too heavy to lift. Inside this sphere, inside the observable universe, astronomers estimate that roughly 200 billion to 2 trillion galaxies exist, each galaxy containing hundreds of billions of stars, each star potentially hosting planets, moons, asteroids, comets. The numbers multiply beyond comprehension. The marble in your hand represents one planet orbiting one star in one galaxy among trillions, and even that description fails because it suggests a numerical relationship that the mind can grasp, when in truth the proportions are so extreme that no metaphor survives contact with them. You are holding a marble, 1 inch, and in a fully scaled marble model of the observable universe, that marble would be one object among septillions. More objects than all the grains of sand on all the beaches of Earth, multiplied by a factor of millions. More objects than every word ever spoken by every human who has ever lived. More objects than any conceivable human endeavour could ever count, ever catalogue, ever comprehend. The scale model breaks entirely here. It does not merely strain, it shatters. The purpose of a scale model is to bring the incomprehensible into the realm of the comprehensible, to translate cosmic proportions into human proportions, to let the feet walk what the mind cannot grasp. But the universe resists such translation. The universe exists at scales so extreme that no model can preserve both accuracy and intuition. You can have one or the other. You cannot have both. And so we return to the solar system. We step back from the galactic precipice, retreat from the cosmic abyss, and settle once more into the parking lot model that we constructed piece by piece. The marble Earth, the peppercorn moon, the tennis ball Mars, the 9-foot sun, the Kuiper belt stretching 19,000 miles in every direction, Proxima Centauri glimmering 6,000 miles away across an ocean of empty space. This is enough. This is comprehensible. This is the model that works, the model that teaches, the model that lets human feet trace cosmic distances and human hands hold planetary proportions. Everything beyond this, the galaxy, the local group, the cosmic web of galactic superclusters strung across the void like dewdrops on a spider's web. Everything beyond requires a different kind of understanding, not spatial, not kinesthetic, something more abstract, more mathematical, more mediated by equations and simulations and trust in instruments that see what eyes cannot. But within the solar system model, within the marble-scale neighbourhood we have constructed together, one truth remains vivid and accessible. The truth of our position, the truth of our location, the truth of where the marble sits in relation to everything else. Earth orbits the Sun at an average distance of 93 million miles. In the marble model, 400 feet. Not at the centre of the solar system, but in the inner reaches, closer to the Sun than to the outer planets, bathed in light and warmth that diminishes rapidly as you move outward. Mercury huddles even closer, 90 feet from the Sun at model scale, a tiny sphere barely half an inch across baking in perpetual noon. Venus floats 200 feet out, slightly smaller than Earth at true scale, a marble's twin cloaked in toxic clouds, and Earth sits at 400 feet, positioned precisely in the zone where water can exist as liquid on a planetary surface, where the temperature neither boils the oceans nor freezes them solid, where the conditions for life as we know it become possible. This is the habitable zone, the Goldilocks region, the orbital sweet spot where a planet receives enough solar energy to sustain liquid water, but not so much that it becomes a pressure cooker like Venus. Earth occupies this zone with a precision that seems almost improbable, given the vastness of space and the randomness of planetary formation. A little closer to the Sun and the oceans would evaporate, a little farther and they would freeze. But Earth sits where it sits, and liquid water flows, and life has flourished for nearly 4 billion years. In the marble model, the habitable zone extends from roughly 200 feet to perhaps 600 feet from the Sun, a band perhaps 400 feet wide within which liquid water planets could theoretically exist. Compare this to the total span of the solar system, the 19,000-mile radius of the heliosphere, and the habitable zone shrinks to almost nothing, a tiny sliver, a narrow groove in a vast circular track. If you threw darts at a map of the solar system, the odds of landing in the habitable zone would be vanishingly small. And yet Earth landed there. Or rather, Earth formed there, aggregating from the swirling disk of gas and dust that surrounded the young Sun 4.5 billion years ago. The laws of physics, the chemistry of the protoplanetary disk, the random collisions of planetesimals and protoplanets, all of these conspired to place our marble precisely where liquid water could persist, where chemistry could complexify, where eventually carbon-based self-replicating molecules could emerge and begin the long climb toward consciousness. The marble in your hand is not merely small, it is also improbably positioned. It occupies a location in space that, within the solar system at least, occurs nowhere else. Mercury is too hot, Venus is too hot, Mars is too cold, though it sits near the outer edge of the habitable zone and may once have been warmer. The outer planets, Jupiter, Saturn, Uranus, Neptune, float in permanent deep freeze, their surfaces, such as they have surfaces, locked in temperatures that would turn any liquid to ice in moments. Earth alone, among the 8 planets, exists in the sweet spot. Earth alone has oceans that flow and storms that rain, and rivers that carve valleys into stone. Earth alone has weather that water participates in, seasons that freeze and thaw, tides that rise and fall under the gravitational pull of a peppercorn moon hanging 2.5 feet away. The marble is special, not cosmically unique perhaps. Astronomers have detected thousands of exoplanets that may occupy habitable zones around their own stars, and the odds favour billions more waiting to be discovered. But within our solar system, within the parking lot model we have constructed, the marble Earth is the only world where you could stand outside without a spacesuit and survive. The only world where rain could fall on your face, and grass could grow beneath your feet, and the sound of wind through trees could reach your ears. This is the context. This is what the scale model reveals when we allow ourselves to consider not just distance but position, not just size but placement. The marble in your hand represents a world that is vanishingly small, desperately isolated, and improbably positioned to harbour life. These three truths compound one another. They multiply. They create a picture of cosmic precariousness that should, by rights, inspire either profound gratitude or profound terror, depending on your disposition. We are small, we are alone, we are lucky, and we are also, in our own way, vast. Because the marble in your hand, small as it is compared to the 9-foot sun, contains multitudes. 7 continents spanning 197 million square miles of land, 361 million square miles of ocean, an atmosphere extending over 300 miles above the surface, thinning gradually into the vacuum of space. Ecosystems ranging from tropical rainforests to Arctic tundra, from abyssal ocean trenches to high alpine meadows, from desert dunes to river deltas to coral reefs blooming with colour. At the 1-inch scale, all of this disappears. The continents become shapes barely visible to the naked eye. The mountains vanish into smooth curves. The oceans become blue smears. The distinction between forest and desert, between city and wilderness, between populated and empty, all of it collapses into the uniform surface of a glass sphere. But the detail is still there. The complexity persists, compressed rather than eliminated. Every inch of the marble surface, if you could zoom in far enough, would reveal layers upon layers of structure. River systems branching like the veins in a leaf, mountain ranges folding like wrinkles in cloth, cities sprawling like bacterial colonies, their streets and buildings too small to see but present nonetheless, and within the cities, the buildings. Within the buildings, the rooms. Within the rooms, the people. 8 billion people. 8 billion human beings living their lives on the surface of that marble. Too small to see at any scale we have discussed. Too numerous to count. Too complex to comprehend. Each one of them waking and sleeping, eating and working, loving and grieving, hoping and fearing. Each one of them carrying within their heads a model of the world, a story of their own existence, a sense of self that feels as vast and important as the cosmos itself. The marble contains multitudes. The marble is not just small, it is also infinitely detailed, endlessly complex, inexhaustibly rich with structure and meaning and life. The scale model shrinks the Earth to something you can hold in your hand, but it cannot shrink what matters about Earth. That remains at full size, tucked inside the glass, invisible but present, waiting to be remembered. This is perhaps the deepest teaching of the scale model. Not just that we are small, though we are. Not just that distances are vast, though they are. But that scale itself is relative. That smallness at one level does not preclude richness at another. That the marble in your hand, for all its insignificance compared to the sun or the galaxy or the observable universe, contains within itself a complexity so profound that no larger structure in the cosmos can match it, as far as we know. The sun is vast, but it is simple, a ball of hydrogen and helium fusing in its core, converting mass to energy, blazing with light that streams outward in all directions. No life dwells within the sun, no ecosystems persist in its plasma, no civilizations have risen and fallen in its convection currents. The sun is large and powerful, and utterly vacant of meaning. The marble is small, but it is complex. Life has flourished on its surface for nearly 4 billion years, evolving from single-celled organisms to the staggering diversity of species that populate the Earth today. Consciousness has emerged, flickering into existence somewhere in the last few million years, looking up at the stars and wondering what they are. And now, in the last few centuries, that consciousness has begun to reach outward, building telescopes and spacecraft, launching probes to other planets, sending radio signals into the void on the off chance that someone might be listening. The marble is small, but the marble thinks. The marble wonders, the marble dreams, and in a universe that, for all we know, may contain nothing else that thinks or wonders or dreams, That fact alone makes the marble precious beyond any measure that size or distance could provide. Now we must leave the marble behind. Not permanently. We will return to it again and again, using it as our anchor, our touchstone, our reminder of where we began. But for now, we must look outward, because the marble does not float alone in the void. Earth has a companion, a partner in its journey through space. A fellow traveller that has accompanied our planet since its violent birth, orbiting faithfully for more than 4 billion years, shaping tides and stabilising seasons, inspiring myths and guiding navigators, hanging in the night sky like a lantern left burning by some cosmic hand. The moon. In our scale model, with Earth shrunk to a 1-inch marble, the moon becomes something you might overlook entirely. A small sphere, roughly 1/4 inch in diameter, about the size of a peppercorn, or a small bead, or the head of a thumbtack. If the Earth is a marble you can hold between your thumb and forefinger, the moon is something you might lose in the seams of your pocket. This immediately reveals something surprising about our celestial companion. The moon is not small in any ordinary sense. Its diameter spans nearly 2,200 miles. You could fit the entire continental United States within its breadth with room to spare. Astronauts who walked on its surface described a world of stark beauty, of ancient craters and boulder-strewn plains stretching to horizons closer than any horizon on Earth. The moon is a world in its own right, massive enough to be spherical, substantial enough to have its own gravitational influence, complex enough to have occupied human imagination since our ancestors first looked up and wondered. But compared to Earth, compared to the marble in your hand, the moon becomes a peppercorn, a small companion for a small world, circling faithfully in the darkness. And yet here is where the first true lesson in cosmic distance begins. Because the question that matters is not just how big the moon appears in our model, but how far away it sits. Picture the marble in your hand again. Earth at 1 inch, the moon at 1/4 inch. How far apart would you hold them to represent the true scale of the Earth-Moon system? Most people, when asked this question, bring their hands close together, perhaps an inch or two. The moon appears so large in our sky, after all. When it rises full over the horizon, it seems to fill our vision, dominating the night with its pale glow. Surely it cannot be that far away. But the moon is not close. The moon is, in fact, startlingly distant. In our scale model, with Earth as a 1-inch marble, the moon would orbit at a distance of approximately 30 inches, 2.5 feet. Stretch out your arm as far as it will go and your fingertips still fall short of where the moon would be. You would need a yardstick held at arm's length to bridge the gap between the marble Earth in your palm and the peppercorn moon hovering at its far end. This is the first great expansion of our imagination. This is where the model begins to teach us something we did not know, something we could not have intuited from our experience of the moon in the sky. The Earth-Moon system is not compact. It is not a planet with a companion hovering nearby, like a parent holding a child's hand. It is a planet with a companion floating in the distance, separated by a gulf of empty space that dwarfs both bodies. Let the numbers sink in. The moon orbits Earth at an average distance of about 239,000 miles. To grasp what this means, consider that the light reaching your eyes from the moon left its surface approximately 1.3 seconds ago. Not much, you might think, a little over a second, barely enough time to blink. But light travels at 186,000 miles per second, the fastest speed allowed by the laws of physics. For light to require more than a second to make the journey tells you something about the space that separates us from our nearest neighbour. When Apollo 11 carried Neil Armstrong and Buzz Aldrin to the lunar surface in July of 1969, the journey took approximately 3 days. 3 days of coasting through the void, with Earth shrinking behind them and the moon growing ahead. 3 days of weightlessness and instrument checks and careful trajectory corrections. 3 days during which the spacecraft covered 239,000 miles of nothing. No air, no sound, no resistance. Just the silent pull of gravity guiding them toward their destination. The astronauts who made this journey reported a peculiar psychological experience. Earth, which had filled their entire lives, which had been the ground beneath their feet, and the sky above their heads, and the horizon in every direction began to shrink. It became something they could see entire, something they could cover with an outstretched thumb. The planet that had seemed infinite that had contained every experience they had ever known, became a fragile blue marble hanging in the darkness, separated from them by a void so vast and so empty that the mind struggled to accept it. And this was just the moon. This was just the peppercorn at the end of the yardstick. This was just the first step outward from the marble in your hand. In our scale model, the Earth-Moon system fits comfortably within a single room. You could set the marble on a table near one wall and place the peppercorn on a table near the opposite wall, and you would have a reasonably accurate representation of the system that ancient civilizations observed and wondered about, the system that modern civilization has actually visited. 8 inches of Earth, 2 inches of Moon, 30 inches of emptiness between them. A model small enough to hold in your mind, small enough to fit in your living room, small enough to seem manageable. But now we must step outside. Now we must leave the room and begin walking. Because the next object in our model, the nearest significant destination beyond the moon, is not inches away. It is not feet away. It is not even in the same building. We're going to Venus. Venus, the second planet from the Sun, Earth's nearest planetary neighbour. Venus, which shines so brightly in the morning and evening sky that ancient civilizations often mistook it for 2 different objects, calling it the morning star and the evening star before realizing they were one and the same. Venus, which orbits so close to the Sun that its surface temperature exceeds 900 degrees Fahrenheit, hot enough to melt lead, hot enough to destroy any spacecraft that has ever attempted to land there within minutes of touchdown. In our scale model, Venus becomes a sphere slightly smaller than Earth, about 0.95 inches in diameter, nearly identical to our marble, just barely distinguishable as slightly smaller. The 2 planets are sometimes called sisters, twins, siblings in the cosmic family. They formed from the same disk of material that swirled around the young sun 4.6 billion years ago. They are made of similar stuff, rock and metal, with atmospheres that once may not have been so different. But Venus took a different path. A runaway greenhouse effect turned it into a furnace. Its thick atmosphere of carbon dioxide traps heat with murderous efficiency. The surface pressure is 90 times greater than Earth's, equivalent to being nearly a mile beneath the ocean. Venus, despite its beauty in our night sky, despite its poetic name, despite its sisterly resemblance to Earth, is a world of utter hostility to life as we know it. How far away is this hostile twin in our scale model? At closest approach, when Venus passes between Earth and the Sun, the 2 planets are separated by approximately 25 million miles. At farthest separation, when Venus is on the opposite side of the Sun, the distance stretches to about 162 million miles. Let us take an intermediate figure, something representative of an average accessible distance, say 30 million miles. In our model, with Earth as a 1-inch marble, 30 million miles becomes approximately 300 feet. 300 feet, the length of a football field. If you set your marble Earth on one goal line and walk to the opposite end zone, you would find Venus waiting for you, another marble of nearly identical size separated from Earth by 100 yards of nothing. This is where the scale model begins to challenge your imagination. This is where the numbers start to resist mental processing, because 300 feet is a distance you can walk in a minute or 2. It is a distance you can shout across if you yell loudly enough. It is a distance that seems small in human terms, trivial, bridgeable, with minimal effort. But remember what the scale represents. Every foot you walk represents 1,000,000 miles. Every step you take represents hundreds of thousands of miles of void, of vacuum, of space utterly hostile to human life. The 3 days it took Apollo astronauts to reach the moon, that journey covered 30 inches in our model. The 100 yards to Venus would require months of travel with current technology, months of coasting through the dark with the sun blazing in the void and Earth shrinking to a point behind you. No human being has ever travelled to Venus. No spacecraft has survived on its surface for more than about 2 hours before the heat and pressure destroyed it. The Soviet Venera program, which landed a series of probes on Venus in the 1970s and 1980s, achieved the only successful surface operations in history. Venera 13, the most successful of these missions, transmitted data for 127 minutes before falling silent. The images it sent back showed a hellscape of flat volcanic rock under an orange sky. The camera and spacecraft slowly being crushed and baked by the hostile environment. And this is our nearest planetary neighbour. This is the closest other world, the sister planet, the object that sometimes passes closer to Earth than any other planet in the solar system. 300 feet in our model, months of travel in reality, 90 atmospheres of pressure, and 900 degrees of heat waiting at the destination. But Venus is not the planet that has captured human imagination most thoroughly. That honour belongs to another world, one that glows red in the night sky, one that has inspired generations of dreamers and scientists, one that has become the focus of humanity's ambitions for becoming a multiplanetary species. Mars. Mars, the red planet, named for the Roman god of war because its rust-coloured surface reminded ancient observers of blood. Mars, which Percival Lowell convinced himself was crisscrossed with canals built by an intelligent civilization, a vision that captured public imagination for decades before spacecraft revealed the truth. Mars, where NASA's rovers have been exploring for years, rolling across dusty plains and climbing ancient mountains, searching for signs that life might once have existed there. In our scale model, Mars becomes a sphere about half the diameter of Earth, approximately 0.53 inches. If Earth is a marble you can hold between your thumb and forefinger, Mars is a bead you might string on a necklace, noticeably smaller but still substantial, still round, still clearly a world rather than a speck. Mars orbits farther from the Sun than Earth does, which means the distance between our two planets varies dramatically depending on where each is in its orbit. At closest approach, when Earth passes between Mars and the Sun, the two planets can come within about 34 million miles of each other. At farthest separation, when they are on opposite sides of the Sun, the distance can exceed 250 million miles. Let us again take a middle figure. Say Earth and Mars are separated by 100 million miles, a reasonable average for mission planning, a distance that represents neither the rarest close approach nor the impossible far separation. In our scale model, 100 million miles becomes approximately 1,000 feet. 1,000 feet! More than 3 football fields laid end to end, about 1/5 of a mile. Stand with your marble Earth in your hand, look down the length of 1,000 feet. That distance, in the real world, is about the length of a large city block. It is the length of a moderate-sized cruise ship. It is the height of the Eiffel Tower. 1,000 feet is a distance you can see, a distance you can walk in a few minutes, a distance that feels achievable and comprehensible. But in our model, that 1,000 feet represents the gulf that any Mars mission must cross. It represents months of travel through the void, with the Sun dwindling to a smaller but still brilliant disk, with Earth shrinking from a world to a dot to something barely visible at all. It represents the journey that curiosity and perseverance made, folded into protective shells, hurtling through the darkness for 7 months before plunging into the thin Martian atmosphere and deploying their parachutes and retro rockets for the terrifying minutes of entry, descent and landing. 7 months to traverse 1,000 feet of model space. 7 months of coasting through nothing, with no possibility of rescue, no opportunity to turn back, no margin for error. The astronauts who will someday make this journey, and they will make it probably within the lifetimes of many people alive today, will experience a psychological challenge unlike any in human history. They will watch Earth disappear behind them, knowing that if anything goes wrong, no help can reach them. They will spend half a year in a small metal container with a handful of companions, falling toward a world that offers no hospitality, no safety, no guarantee of return. And when they arrive, what will they find? A world of rust-red deserts and ancient river valleys, of towering volcanoes and vast canyons, of thin atmosphere and bitter cold. Mars is not Earth's twin. Mars is Earth's reminder of what can go wrong. Once, perhaps, Mars had liquid water on its surface. Once, perhaps, Mars had a thicker atmosphere that could have supported something like life. But Mars is smaller than Earth. It lost its internal heat faster. Its magnetic field died, and without that shield, the solar wind stripped away its atmosphere over billions of years. What remains is a world in suspended animation, frozen at some point in its decline, waiting for whatever comes next. From Mars, Earth would be visible as a bright blue star in the Martian sky. The Curiosity rover has photographed it, a pale blue dot hovering above the horizon, indistinguishable from a star except that instruments tell us otherwise. From 1,000 feet away in our model, Mars could look at Earth and see a marble, and Earth could look at Mars and see a bead, and the gulf between them would seem trivial, just a short walk across a parking lot or a city block. But the gulf is not trivial. The gulf is months of travel. and billions of dollars and risks so profound that every Mars mission represents a triumph of engineering and courage. The gulf is 100 million miles of vacuum, 100 million miles of radiation, 100 million miles of silence. Now we must turn our attention away from our small rocky neighbours and towards something far larger, far brighter, far more dominant. We have been orbiting the Sun this entire time, spinning around it in our yearly circuit, warmed by its light, governed by its gravity. But we have not yet placed the Sun in our model. We have not yet asked the question that will truly begin to strain our imagination. How far away is the Sun? The Sun is not like the planets. The Sun is not a small rocky world or a modest gas giant. The Sun is a star, a nuclear furnace of such immense power that it contains 99.86% of all the mass in the entire solar system. Everything else, all the planets, all the moons, all the asteroids and comets and dust, amounts to a rounding error, a thin film of debris orbiting around the massive gravitational centre that holds everything together. In our scale model, with Earth as a 1-inch marble, the Sun becomes a sphere approximately 9 feet in diameter. 9 feet. The height of a basketball hoop. Nearly as tall as a single-storey house. If you stood next to a sphere 9 feet across, it would tower above you, massive and imposing and impossible to ignore. This is the first truly jarring adjustment the model requires. We have been working with small objects, marbles and peppercorns and beads, objects you can hold in your hand, objects you can comprehend at a glance. But the Sun refuses to fit in your hand. The Sun requires you to step back, to tilt your head, to take in something that dwarfs you physically. And yet the Sun, for all its enormity, is not nearby. Earth orbits the Sun at an average distance of approximately 93 million miles, a distance so commonly referenced in astronomy that it has its own name, the astronomical unit, abbreviated AU, 1 AU, the measuring stick for everything within our solar system, the distance that light covers in about 8 minutes and 20 seconds. 8 minutes and 20 seconds. The light streaming through your window right now left the Sun's surface 500 seconds ago. If the Sun vanished at this precise moment, you would have no idea for another 8 minutes. You would continue to feel its warmth, see its light, orbit around the space where it had been, all without knowing that it was gone. The universe would have changed fundamentally, and you would remain ignorant going about your day waiting for news that travels at the fastest speed possible, but still requires more than 8 minutes to cross the void. In our scale model, 93 million miles becomes approximately 932 feet. Let us round to 900 feet for simplicity. 900 feet. 3 football fields. 3/10 of a mile. The length of a very long city block, or a short walk through a park, or the distance you might cover in a 2-minute jog. Place your 1-inch marble Earth in your hand. Place the 9-foot Sun 900 feet away from you. Between them lies nothing but model space. The same nothing that fills the real space between Earth and Sun, the vacuum through which photons and solar winds stream outward in all directions. This image, more than any other, captures something essential about our solar system. We are not close to the Sun. We are not huddled near the fire, basking in its warmth from a comfortable distance. We are standing nearly 1,000 feet from a 9-foot furnace, catching whatever light and heat happens to stream in our direction, and calling it comfortable, calling it perfect, calling it the Goldilocks zone, neither too hot nor too cold, just right for liquid water and life. But this model also reveals something else. The 9-foot Sun, 900 feet away, would appear small from where you stand. Do the geometry. At 900 feet of distance, a 9-foot object subtends an angle of approximately half a degree. Half a degree is almost exactly the apparent size of the Sun in our actual sky. The model preserves not just the absolute sizes and distances, but the visual relationships, the way things appear to us as we stand on our marble and look outward. The Sun that rises and sets each day. The Sun that fits behind your thumb when you hold it at arm's length. The Sun that seems so manageable and comprehensible from the surface of Earth. That Sun is 9 feet across and 900 feet away in our model. It is a furnace of nuclear fire fusing 620 million tons of hydrogen into helium every second, converting 4 million tons of matter directly into energy with each tick of the clock, pouring that energy outward into the void, where Earth intercepts less than 1/1000th of the total output. Less than 1/1000th. And still the Sun powers every ecosystem on Earth. Still the sun drives the weather and the ocean currents and the cycles of warmth and cold that govern all life. Still the sun's energy, captured by plants and converted into chemical bonds, fuels every animal that walks or swims or flies, every human being who eats and breathes and thinks. 1/1000th of the sun's output, falling on a 1-inch marble 900 feet away, sustains everything we have ever known. You could walk from the Earth to the sun in our model in perhaps 5 minutes, a leisurely stroll across 3 football fields. But in reality, that journey would take months. The Parker Solar Probe, launched in 2018 and designed to study the sun's outer atmosphere, will eventually come within about 4 million miles of the solar surface, closer than any spacecraft in history. Even at that close approach, it will still be 40 feet away from the 9-foot sun in our model, and reaching that proximity requires years of gravitational assists and trajectory adjustments, looping repeatedly around Venus to shed orbital energy and spiral inward. The sun dominates everything. The sun is 99.86% of the mass. The sun's gravity holds the planets in their orbits, keeps the asteroids from dispersing into the void, captures comets that fall in from the outer darkness, and yet the sun is far. 900 feet of nothing separate us from our parent star, and that nothing is filled with radiation that would kill any unprotected human in minutes. We have now placed 3 objects in our model: the 1-inch Earth, the 1/4-inch Moon 30 inches away, and the 9-foot sun 900 feet distant. We have placed Venus and Mars in their approximate positions, 300 feet and 1,000 feet from Earth respectively, depending on orbital configurations. Already the model has grown beyond the scale of a table or a room. Already it requires outdoor space, a field or a parking lot, a stretch of ground long enough to accommodate the inner solar system. But the inner solar system is small. The inner solar system is the warm, rocky zone close to the sun, where worlds like Mercury and Venus and Earth and Mars formed from heavier elements that could survive the young sun's heat. Beyond Mars lies the asteroid belt, and beyond the asteroid belt lie the giants: Jupiter and Saturn, Uranus and Neptune. These worlds are not close. These worlds are not a short walk across a field. These worlds will stretch our model beyond anything we've imagined so far. The peppercorn moon at arm's length was surprising. Venus at 100 yards was sobering. Mars at 1,000 feet was daunting. But we have barely begun. We have taken the first few steps on a journey that will carry us miles before we reach the edge of the sun's domain. The model that fit in a room, that seemed manageable and comprehensible, is about to become something else entirely. It is about to become a walk through the neighbourhood, then through the town, then out into the countryside, until the 1-inch marble in your hand becomes a memory rather than a visible object, a starting point too distant to see. This is the nature of the solar system. This is the truth that no photograph can convey. No planetarium show can truly communicate. No casual understanding of space can accommodate. The solar system is mostly empty. The planets are specks. The distances between them are vast beyond any intuitive grasp, and we are just getting started. Jupiter lies beyond the asteroid belt, beyond the cold boundary where the young sun's heat could no longer vaporize ice, beyond the region where rocky worlds give way to gas giants. In our model, Jupiter sits approximately 4,400 feet from the sun, not 4,400 feet from the Earth, 4,400 feet from the 9-foot blazing sphere we placed at the centre of everything. That is nearly a mile. That is 17 football fields laid end to end. That is a walk that would take you perhaps 12 to 15 minutes at a comfortable pace, assuming flat terrain and no obstacles, assuming you simply put one foot in front of the other and kept moving through the emptiness. Picture it. You're standing next to the 9-foot sun, its surface roiling with imaginary fire, its mass so dominant that everything else in the solar system seems almost incidental. You begin walking. You pass the position where Mercury would orbit, a tiny sphere smaller than a pea, perhaps 50 feet from the sun. You pass Venus, a marble slightly smaller than Earth, at about 110 feet. You pass Earth itself at 160 feet, 1 inch of blue and white and green, impossibly fragile, impossibly small. You pass Mars at 240 feet, a peppercorn dusted with rust. You keep walking. You enter the asteroid belt, that diffuse ring of rocky debris where a planet might have formed but never did, scattered by Jupiter's gravitational influence before it could coalesce. The asteroid belt stretches from roughly 350 feet to 600 feet from the sun in our model, a band of space where billions of objects orbit, but where the total mass of all those objects combined is less than 4% of the Moon's mass. If you gathered every asteroid in the belt into a single sphere, it would be smaller than our Moon. The asteroid belt is not a hazard. The asteroid belt is not the dense field of tumbling rocks depicted in science fiction films. The asteroid belt is empty. The typical distance between large asteroids is millions of miles. Spacecraft pass through the asteroid belt routinely, and the odds of striking anything are vanishingly small. In our model, the asteroid belt is a 250-foot wide zone containing almost nothing visible to the naked eye. You keep walking. You leave the asteroid belt behind. The inner solar system is now hundreds of feet behind you. The 9-foot Sun, which seemed so dominant when you stood beside it, is beginning to shrink in your perception. At 500 feet it would still appear enormous, but you have walked far past that now. At 1,000 feet the Sun would be the height of a person seen from 1,000 feet away. Noticeable, but no longer overwhelming. At 2,000 feet the Sun would be the size of a small child, viewed across the length of 2 football fields. At 3,000 feet the Sun would be shrinking toward the size of a basketball seen from nearly half a mile away. And still you would have another 1,400 feet to walk before reaching Jupiter. When you finally arrive, you find a sphere roughly 11 inches in diameter, nearly a foot across. After all those specks and pebbles, all those peppercorns and marbles, Jupiter is the first object since the Sun that feels substantial. Jupiter is large enough to see clearly from a distance. Jupiter is large enough to hold in both hands to feel the weight and presence of a true giant. And this is precisely how Jupiter appears in the actual solar system, the first world you encounter after leaving the inner planets that seems genuinely massive. Jupiter contains more mass than all other planets combined. Jupiter contains 318 times the mass of Earth. If you could line up Earth side by side across Jupiter's equator, you would need 11 of them. If you could fill Jupiter's volume with Earth's, you would need 300 of them. But here is what the model reveals that photographs cannot. Jupiter is far. Jupiter is not merely larger than the inner planets. Jupiter is also much, much more distant. The gap between Mars and Jupiter is greater than the entire span from the Sun to Mars. You walk 240 feet to reach Mars from the Sun. You walk another 4,060 feet to reach Jupiter from Mars. The inner solar system is a suburb clustered close to the central star. The outer solar system is a wilderness stretching beyond imagination, and Jupiter is merely the first outpost in that wilderness. In reality, light from the Sun takes approximately 43 minutes to reach Jupiter. Radio signals from Earth to Jupiter, travelling at the ultimate speed limit of the universe, require between 33 and 53 minutes, depending on the orbital positions of both planets. When the Juno spacecraft entered orbit around Jupiter in July 2016, the signal confirming successful orbital insertion took 48 minutes to reach Earth. For those 48 minutes, the spacecraft's fate was already sealed. Either it had succeeded or it had failed, but the engineers at the Jet Propulsion Laboratory had no way to know which. They waited, staring at screens while light crawled across the solar system. The event had already happened. They simply had to wait for the news to arrive. This is what distance means. This is what the model makes visceral. You can walk from the Sun to Jupiter in 12 or 15 minutes. Light, the fastest thing in the universe, requires 43 minutes to make the same journey. The scale of time and space in the solar system exceeds anything human beings evolved to comprehend. We evolved on a planet where the horizon is 3 miles away, where sound travels fast enough to warn of predators, where events and their perception are essentially simultaneous. We evolved in a world of seconds and minutes, where the sun rose each morning and set each evening, where the stars wheeled overhead in patterns unchanging across human lifetimes. We did not evolve to understand that light itself is slow when measured against cosmic distances. We did not evolve to understand that the sun we see in the sky is the sun as it was 8 minutes ago, that the Jupiter we observe through telescopes is Jupiter as it was between half an hour and an hour ago. The present moment, as we perceive it, is a fiction maintained by the fortunate circumstance that our sensory world is small enough for light to cross it instantaneously by human standards. Saturn lies beyond Jupiter, the second of the gas giants, the ringed wonder that has captivated human observers since Galileo first glimpsed its strange shape through his primitive telescope in 1610. Galileo could not resolve what he was seeing. He described Saturn as having ears, or appearing triple-bodied. It was not until 1655 that Christian Huygens, using a more powerful telescope of his own design, correctly identified Saturn's rings as a flat disk surrounding the planet. In our model, Saturn sits approximately 8,100 feet from the Sun. 8,100 feet. That is more than a mile and a half. That is the length of roughly 27 football fields. That is a walk that would take you between 25 and 30 minutes at a steady pace. You have already walked nearly a mile to reach Jupiter. Now you must walk another 3/4 of a mile beyond Jupiter to reach Saturn. The outer solar system is spreading apart, each subsequent planet more distant from its predecessor than the last, the gaps widening as you move outward from the Sun. Saturn itself is slightly smaller than Jupiter in our model, perhaps 9 inches in diameter compared to Jupiter's 11. But Saturn's rings extend far beyond the planet's surface, stretching outward to perhaps 18 inches or more in our model. The rings are not solid. The rings are composed of billions of particles ranging in size from grains of sand to chunks of ice the size of houses. The rings are thin, astonishingly thin relative to their breadth. If you scaled Saturn's rings to the diameter of a football field, they would be about 1 inch thick. In our model, the rings would be thinner than a sheet of paper, yet they would extend nearly 1.5 feet in all directions. The rings are a phenomenon of almost pure two-dimensionality, a vast disk of orbiting debris so flattened that it seems impossible such a structure could exist. And yet it does. And yet it has existed for millions or perhaps billions of years, maintained by the complex interplay of Saturn's gravity, the gravitational influence of Saturn's many moons, and the orbital mechanics that keep particles sorted into distinct bands and gaps. You're now standing more than a mile and a half from the Sun. The 9-foot sphere that dominated the centre of our model is now a distant object, visible but small. From this distance, the Sun would appear perhaps 3 inches across, the size of a tennis ball viewed from 8,100 feet away. The warmth, the overwhelming presence, the sense of being close to the engine that drives everything, all of that is gone. Saturn receives approximately 1% of the sunlight that Earth receives. The noon sun on Saturn is 100 times dimmer than the noon sun on Earth. At Saturn's distance, the Sun provides about as much illumination as 100 full moons on Earth. Enough to see clearly, enough to cast shadows, but nothing like the blazing brilliance we experience on our world. Saturn is cold. Saturn's cloud tops average minus 288 degrees Fahrenheit, cold enough to freeze not just water, but ammonia. Saturn is a world of pale gold clouds and violent storms, of hexagonal polar vortices and winds that blow at 100 miles per hour. And Saturn is remote. Saturn is so distant that spacecraft require years to reach it. The Cassini mission, launched in October 1997, did not arrive at Saturn until July 2004. 7 years of travel. 7 years of falling through the void, using gravitational assists from Venus, Earth, and Jupiter to build up the velocity needed to reach the outer solar system. Cassini spent 13 years studying Saturn before deliberately plunging into the planet's atmosphere in September 2017, ensuring that the spacecraft would not contaminate Saturn's potentially habitable moons. Cassini's final signal took 83 minutes to reach Earth. For 83 minutes, Cassini was already destroyed, already vaporized in Saturn's crushing depths, but the engineers and scientists who had spent decades on the mission did not yet know. They waited, they watched their screens, and then the signal stopped, and they knew their spacecraft was gone. This is distance. This is what it means to operate in the outer solar system. This is the truth our model makes palpable. Beyond Saturn lies Uranus, the first planet discovered in the modern era, the first planet found with a telescope rather than known from antiquity. William Herschel spotted Uranus in March 1781 while conducting a systematic survey of the night sky from his garden in Bath, England. He initially believed he had found a comet. It was only after months of observation, after calculating the object's orbit and determining that it was nearly circular rather than the elongated path typical of comets, that astronomers accepted Uranus as a new planet. The first planet discovered in recorded history, doubling the known size of the solar system overnight. In our model, Uranus sits approximately 16,000 feet from the Sun. 16,000 feet. That is 3 miles. 3 miles from the Sun to Uranus, most of that distance empty and dark and cold. Uranus itself is about 4 inches in diameter in our model, larger than Earth, smaller than Saturn, a middle-sized world often overlooked in our fascination with the true giants. Uranus is strange. Uranus rotates on its side, its axis tilted 98 degrees from the plane of its orbit, so that its poles alternately point toward and away from the Sun during its 84-year orbital period. One pole experiences 42 years of continuous sunlight, while the other experiences 42 years of continuous darkness. The reason for this extreme tilt remains uncertain, but the leading hypothesis suggests a collision with an Earth-sized object early in the solar system's history, a cataclysm that knocked the young planet onto its side and left it spinning like a top rolling along its orbital path. You have now walked 3 miles. The Sun is a distant memory, a small bright point in the sky behind you, providing barely any warmth at all. Uranus receives only 1/400th of the sunlight that Earth receives. The temperature in Uranus's upper atmosphere drops to minus 357 degrees Fahrenheit, making it the coldest planetary atmosphere in the solar system, colder even than Neptune, which is farther from the Sun. Uranus radiates very little internal heat compared to the other giant planets, so it lacks the internal energy source that helps warm Jupiter and Saturn and Neptune from within. Uranus is a cold, tilted, enigmatic world, and only one spacecraft has ever visited it, Voyager 2, which flew past in January 1986 after a journey of more than 8 years from Earth. Neptune waits beyond Uranus, the last of the giant planets, the outermost major world in our solar system. Neptune was the first planet discovered through mathematics rather than observation. In the 1840s, astronomers noticed that Uranus was not following its predicted orbital path. Something was tugging on it, some unseen mass exerting gravitational influence from beyond. 2 mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently calculated where this unseen planet must be. In September 1846, astronomers at the Berlin Observatory pointed their telescope at the position Le Verrier had predicted, and found Neptune within 1 degree of the calculated location. The discovery was a triumph of Newtonian mechanics, proof that the laws of gravity could reveal the presence of worlds too distant and too dim to find by chance. In our model, Neptune sits approximately 25,000 feet from the Sun. 25,000 feet! That is nearly 5 miles. 5 miles of walking from the centre of our model to reach the 8th and outermost planet. Neptune itself is roughly the same size as Uranus in our model, about 4 inches in diameter, but Neptune is far more dynamic. Neptune has the strongest winds in the solar system, howling at speeds up to 1,200 miles per hour. Neptune is a brilliant azure blue, its colour produced by methane in its atmosphere, absorbing red light and reflecting blue. Neptune has a large moon, Triton, which orbits the planet backwards, a retrograde orbit suggesting that Triton was captured from the Kuiper Belt, rather than forming alongside Neptune. 25,000 feet. You have walked nearly 5 miles from the Sun. The journey has taken you perhaps an hour and a half at a steady walking pace, more if you pause to contemplate the emptiness between worlds. The Sun is now a small bright point, perhaps 1 inch in apparent diameter seen from this distance, providing approximately 0.09% of the light it provides to Earth. Neptune receives less than 1,000th of Earth's sunlight. Noon on Neptune is darker than deep twilight on Earth, a perpetual dusk where the Sun is merely the brightest star in a sky full of stars. Only one spacecraft has ever visited Neptune, Voyager 2, the same spacecraft that visited Uranus 3 years earlier. Voyager 2 flew past Neptune in August 1989, 12 years after its launch from Earth. The spacecraft's radio signals, travelling at the speed of light, took over 4 hours to reach Earth. When Voyager 2 encountered Neptune, it was so far from the Sun that the light levels were 900 times dimmer than at Earth. The spacecraft's cameras, designed primarily for the brighter inner solar system, had to take long exposure images to capture Neptune's cloud bands and storms. The engineering challenges were immense. The triumph was extraordinary. We have now reached the edge of the traditional planetary solar system. We have walked 5 miles from a 9-foot sun, past pebbles and marbles and gas giants, past worlds of fire and ice and wind. But we have not reached the edge of the Sun's domain. We have not even come close, because beyond Neptune lies something larger than everything we have encountered so far. Beyond Neptune lies the Kuiper Belt. The Kuiper Belt is a vast ring of icy objects, debris left over from the formation of the solar system, material that never coalesced into a planet because Neptune's gravity scattered it before aggregation could occur. The Kuiper Belt begins near Neptune's orbit and extends outward to approximately 50 astronomical units from the Sun, 50 times the Earth-Sun distance. In our model, the Kuiper Belt stretches from approximately 25,000 feet to 40,000 feet from the Sun. That outer edge is more than 7.5 miles from where we started. Pluto orbits within the Kuiper Belt at an average distance of about 31,000 feet from the Sun in our model, nearly 6 miles out. Pluto, once considered the 9th planet, now classified as a dwarf planet, is tiny, less than 1/5 of an inch in our model, smaller than the Moon, smaller than 7 moons orbiting other planets. Pluto is a speck in the darkness, a frozen world where the noon sun appears merely as a bright star, where temperatures hover near -375 degrees Fahrenheit, where nitrogen ice flows in glaciers and frozen mountains of water ice rise miles high. The New Horizons spacecraft launched in January 2006 and reached Pluto in July 2015, 9.5 years of travel to cross the void between Earth and the Kuiper Belt. When New Horizons flew past Pluto at 31,000 miles per hour, its signals took 4.5 hours to reach Earth. The images it returned revealed a world of unexpected complexity: mountains, plains, glaciers, haze layers, and a heart-shaped basin of nitrogen ice that became instantly iconic. We had expected a dead, cratered ball of ice. We found something far stranger and far more beautiful. But Pluto is merely one object among trillions in the Kuiper Belt. The Kuiper Belt contains an estimated 100,000 objects larger than 60 miles in diameter. It contains billions of smaller objects, chunks of ice and rock ranging from pebbles to mountains, all orbiting in the dim twilight beyond Neptune. The total mass of the Kuiper Belt is perhaps 25 to 30 times the mass of the asteroid belt. Still small by planetary standards, but vast in terms of the sheer number of objects. In our model, the Kuiper Belt is a diffuse ring 15,000 feet wide, a band of space stretching from 6 miles out to 7.5 miles out, filled with countless specks too small to see and too numerous to count. You have walked 7.5 miles. The Sun is almost unrecognizable now, a mere pinpoint of light that your hand could easily eclipse. The 1-inch Earth is 6 miles behind you, invisible, inconceivable, a mote swallowed by distance. The gas giants, Jupiter and Saturn and Uranus and Neptune, are scattered along the miles you have traversed. Their substantial size is reduced by distance to irrelevance. Everything you have ever known, everything human civilization has ever touched, lies within a sphere smaller than a few miles across in this model. And beyond you, beyond the edge of the Kuiper Belt, lies something larger still. Beyond the Kuiper Belt lies the scattered disk, a region of objects with highly elliptical orbits that carry them far above and below the plane of the solar system. Beyond the scattered disk lies the theoretical Oort cloud, a spherical shell of comets and icy bodies extending perhaps 1 or 2 light years from the Sun, halfway to the nearest star. In our model, the Oort cloud would extend 2,500 miles in every direction, not feet, miles. The Oort cloud would encompass a sphere 5,000 miles across, centred on our 9-foot Sun. From our starting point in the centre, the inner edge of the Oort cloud would begin at approximately 50 miles out, and its outer edge would stretch to 2,500 miles, roughly the distance from New York to Los Angeles. This is the true extent of the Sun's domain. This is the boundary where solar gravity finally yields to the gravitational influence of other stars. This is where the solar system ends and interstellar space begins. And in all that vastness, in all those miles and thousands of miles, there is almost nothing. A handful of planets, a scattering of moons, a diffuse ring of icy debris, and darkness. Darkness and cold and silence extending beyond comprehension. The darkness you stand in now is unlike any darkness Earth can offer. This is not the darkness of a moonless night, not the darkness of a cave, not the darkness of closed eyes. This is the darkness of the void itself, a darkness so complete that the very concept of light becomes an abstraction, a distant memory of warmth that barely registers against the endless cold. You have walked 7.5 miles from a 9-foot Sun. You have traversed the entire classical solar system, from Mercury's scorched orbit to Pluto's frozen exile. You have witnessed the scale of worlds shrink from the magnificent to the minuscule, and you have felt the distances grow from the manageable to the incomprehensible. But everything you have experienced so far, every mile you have walked, every planet you have passed, every moon and asteroid and comet you have catalogued, all of it amounts to nothing more than the first step of a far longer journey. The nearest star beckons. Alpha Centauri lies 437 light-years from Earth. This number, spoken casually in countless documentaries and textbooks, deserves to be understood in the terms we have established. A light-year is the distance light travels in 1 year, approximately 5.88 trillion miles. Alpha Centauri, therefore, lies approximately 25.7 trillion miles from our Sun. In our model, where the Sun is 9 feet across and the Earth is a 1-inch marble 6 miles away, Alpha Centauri lies roughly 49,000 miles from where you stand. Let this distance settle into your mind. You have walked 7.5 miles to reach the outer edge of the Kuiper Belt. To reach the nearest star in our model, you would need to walk 49,000 miles. This is nearly twice the circumference of the actual Earth. This is the distance from New York to Sydney and back, repeated 12 times. This is walking a marathon every day for 5 years straight, and Alpha Centauri is the nearest star, the closest stellar neighbour our Sun possesses. The vast majority of stars visible in the night sky lie tens, hundreds, or thousands of times farther away. The galaxy itself spans 100,000 light-years. In our model, the Milky Way would be over 1 billion miles across, larger than the actual orbit of Jupiter around the actual Sun. The void between stars defies every instinct we possess about distance and proximity. Our brains evolved to navigate environments measured in steps and arm lengths, to track prey across savannas and remember paths through forests. We can imagine a mile, perhaps several miles, perhaps even the distance of a cross-country drive. But 49,000 miles of empty space, with nothing, absolutely nothing, to break the journey. This is not a distance the human mind can truly grasp. It can only stand at the edge and stare into the abyss, knowing intellectually that the abyss continues far beyond the horizon of imagination. Consider what those 49,000 model miles contain. Between your current position at the edge of the Kuiper Belt and the nearest star lies the outer solar system, the Oort cloud, and then interstellar space proper. The Oort cloud, as we noted, extends perhaps 2,500 miles in our model. This means that after passing through the Oort cloud, after walking 2,500 miles from the edge of the Kuiper Belt, you would still have approximately 4,600 miles to go before reaching Alpha Centauri. The Oort cloud, vast beyond imagination, represents merely 5% of the distance to the nearest star. And what fills those 4,600 miles? Almost nothing. A few rogue objects, perhaps. Interstellar comets and asteroids drifting between star systems, too faint and too cold to detect. Interstellar dust, particles of carbon and silicon and iron scattered so thinly that a cubic mile of interstellar space contains less matter than exists in a single breath of air. Cosmic rays, high-energy particles racing through the void at nearly the speed of light. The debris of stellar explosions and the exhaust of distant black holes. Magnetic fields, attenuated and weak. The fading influence of our Sun giving way to the fading influence of other stars. But in terms of substance, in terms of anything you could see or touch or stand upon, there is nothing. The interstellar medium contains approximately 1 atom per cubic centimetre on average. 1 atom, in a space the size of a sugar cube. The best vacuum chambers ever created on Earth contain roughly 100,000 atoms per cubic centimetre. Interstellar space is 100,000 times more empty than the most perfect artificial vacuum human technology can produce. If you could somehow survive the journey through our model, walking those 49,000 miles from the Sun to Alpha Centauri, you would spend 46,000 of those miles in a void more complete than anything we have ever manufactured. This is why we call it space. Not the darkness, not the cold, not the radiation. The space itself. The sheer, absolute crushing emptiness between things. Let us attempt to make this tangible through time rather than distance. In our model, light travels at approximately 1.4 miles per hour, a leisurely walking pace. A beam of light leaving our 9-foot Sun would reach the 1-inch Earth in about 4.25 hours of model time. It would reach the 1/2-inch Jupiter in just under a day. It would reach the 1/4-inch Neptune in 2.5 days, and it would reach Alpha Centauri in approximately 437 years, the same 437 years it takes in reality, because our model preserves the ratios perfectly. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object from Earth. As of now, Voyager 1 is approximately 15 billion miles from the Sun, travelling outward at roughly 38,000 miles per hour. In our model, Voyager 1 is about 12 miles from the central Sun, having just passed through the heliopause and entered interstellar space. 12 miles in 47 years of continuous travel. To reach Alpha Centauri at its current speed, Voyager 1 would require approximately 73,000 years. In our model, that would be 73,000 years of walking at its pace to cover 49,000 miles. A human walking at 3 miles per hour could cover the same distance in about 16,000 hours of continuous walking. Roughly 2 years of walking without rest, without sleep, without pause. But of course, no human could walk continuously for 2 years. And no human could survive the journey in reality, because the journey in reality spans not 49,000 model miles, but 25.7 trillion actual miles. The fastest spacecraft ever launched, the Parker Solar Probe at its closest approach to the Sun, achieves speeds of approximately 430,000 miles per hour. At that speed, which cannot be maintained outside the Sun's gravitational influence, reaching Alpha Centauri would still require roughly 6,100 years. The Great Pyramid of Giza was completed approximately 4,500 years ago. A spacecraft travelling at Parker Solar Probe speeds, launched when the Great Pyramid was being built, would still be less than 2/3 of the way to Alpha Centauri today. The stars are close enough to see, but far enough to be forever unreachable by any technology we currently possess. This is the fundamental truth that our model reveals, the truth that no amount of wishful thinking or science fiction can fully erase. The universe is not merely large. It is large in a way that makes human scales, human speeds, human lifetimes, human civilizations vanish into statistical insignificance. Yet Alpha Centauri is merely the closest port in an infinite harbour. The solar neighbourhood, the region of space within approximately 50 light-years of the Sun, contains roughly 2,000 stars. In our model, this neighbourhood would extend 560,000 miles from our central Sun, a sphere large enough to encompass the actual Moon's orbit around the actual Earth. Within this sphere, 2,000 stars float in isolation, each separated from its neighbours by tens of thousands of model miles. Some of these stars are larger than our Sun and would appear as spheres 10, 15 or 20 feet across in our model. Some are smaller, red dwarfs that would shrink to beach balls or basketballs. Many have planets of their own, worlds we are only beginning to detect, places where the same laws of physics play out in arrangements we have never seen. Proxima Centauri, the closest of the 3 stars in the Alpha Centauri system, is a red dwarf roughly 1/7 the diameter of our Sun. In our model, Proxima Centauri would be a sphere about 15 inches across, roughly the size of a beach ball. This beach ball star would float approximately 48,000 miles from our 9-foot Sun, attended by at least 3 known planets. Proxima Centauri b, the most Earth-like of these worlds, orbits its star at a distance of approximately 4.7 million miles, about 1/20th the distance from Earth to our Sun. In our model, Proxima b would be less than half an inch across, orbiting its beach ball star at a distance of roughly 200 feet. Imagine standing on Proxima b if it has a surface at all, if it has not been sterilized by the violent flares that red dwarf stars are prone to emit. You would see a sun far dimmer than ours, reddish in hue, looming larger in the sky because of your proximity, but providing less light, less warmth, less of the familiar solar presence that has shaped all terrestrial life. Your year would last only 11 Earth days. Your sky might glow with auroras more frequently than Earth's, as stellar flares bombard your world with charged particles. And somewhere in that alien sky, if you knew where to look, you might find a faint yellow star, our Sun, appearing no brighter than we see Jupiter on a clear night. Earth would be invisible, a mote too small and too close to that yellow pinpoint to detect with any eye. The knowledge that such worlds exist, that they orbit in what astronomers call the habitable zone, that they might possess liquid water and the preconditions for life, is among the most profound discoveries of recent decades. But the knowledge cuts both ways. These worlds exist, they are real, and they are 25 trillion miles away, separated from us by a void that no human being will cross in our lifetimes, or our children's lifetimes, or perhaps in any lifetime for centuries to come. Let us continue outward in our imagination, past Alpha Centauri, past the immediate solar neighbourhood, into the broader structure of the galaxy itself. The Milky Way is a barred spiral galaxy approximately 100,000 light-years in diameter. It contains somewhere between 100 billion and 400 billion stars, each star separated from its neighbours by light-years of emptiness. The Sun lies approximately 26,000 light-years from the galactic centre, about halfway out from the core to the rim, in a relatively sparse region between two major spiral arms. In our model, where 1 astronomical unit equals 6 miles, and 1 light-year equals approximately 11,200 miles, the Milky Way would be over 1 billion miles across. This is larger than the actual orbit of Saturn around the actual Sun. The galactic centre would lie approximately 290 million miles from our position, roughly the distance from the actual Sun to the actual asteroid belt. We are truly in the galactic suburbs, far from the crowded stellar cities of the core, far from the ancient stars that cluster around the central supermassive black hole. The structure of the galaxy, when visualized at this scale, reveals both pattern and chaos. The spiral arms that seem so elegant in photographs are not solid structures, but density waves, regions where stars and gas and dust bunch together temporarily before drifting apart over millions of years. The Sun has orbited the galactic centre approximately 20 times since its formation 4.6 billion years ago. Each orbit takes roughly 230 million years. The dinosaurs ruled Earth for about 165 million years, less than a single galactic year. All of human history, every civilization, and every empire, and every technological achievement has occurred during less than 1,000% of a single galactic rotation. And the Milky Way itself is merely one galaxy among hundreds of billions. The Andromeda Galaxy, our nearest large galactic neighbour, lies approximately 2.5 million light-years away. In our model, Andromeda would be over 28 billion miles distant, farther than the actual distance from the Sun to the actual Voyager 1, multiplied by nearly 2,000. We cannot walk this distance in imagination. We cannot truly conceive it. We can only know, abstractly, that the universe contains structures separated by voids that dwarf the void between stars as thoroughly as the void between stars dwarfs the void between planets. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, spans approximately 93 billion light-years in diameter. This is not the entire universe, it is merely the portion we can see. Beyond the observable universe, space continues, perhaps infinitely, containing galaxies and stars and worlds we will never detect because their light has not had time to reach us and never will. In our model, the observable universe would be over 1 quadrillion miles across. This number is meaningless. It is too large to write, too large to imagine, too large to do anything but gesture toward and then look away. But let us return to something almost comprehensible. Let us return to our 1-inch Earth, our 6-mile distance to a 9-foot Sun, our 49,000-mile journey to the nearest star. Let us consider what it would mean to actually traverse this distance, to leave the solar system behind and venture into the void. The challenges are not merely technological, they are existential. An interstellar spacecraft would need to survive conditions that no human engineering has ever faced for the durations that would be required. It would need to navigate through a void where no assistance is possible, where any malfunction is terminal, where communication delays stretch from minutes to hours to days to years. A spacecraft travelling to Alpha Centauri at 10% of the speed of light, far faster than any spacecraft we have ever built, would require 44 years to reach its destination. Messages sent home would take 4.37 years to arrive. Responses would take another 4.37 years to return. A conversation with mission control would have gaps of nearly 9 years between exchanges. The crew of such a mission, if there were a crew, would age 44 years during their journey. They would leave as young adults and arrive as elderly individuals, having spent their entire professional lives in transit, having missed every birth and death and wedding and funeral among their families and friends, having become strangers to a civilization that would have changed beyond recognition during their absence. The Earth they left would be as different from the Earth they departed as our world today is different from the world of 1980. Technologies would have advanced, governments would have risen and fallen, the people who waved goodbye at launch would be dead or dying. This is the price of interstellar travel at speeds even remotely achievable by physics as we understand it. The distances are simply too vast for any human lifetime to contain comfortably. We are not merely far from the stars, we are separated from them by gulfs of time as much as gulfs of space. And yet the stars shine in our sky every night. They have shone since the first humans looked upward and wondered. They will continue to shine long after human civilization has run its course, long after the sun has swelled into a red giant and swallowed the inner planets, long after the Milky Way and Andromeda have merged into a single elliptical galaxy, and the last stars have exhausted their fuel and faded into darkness. The universe does not care about human scales. It did not arrange itself for our convenience. It was not designed to be crossed or comprehended or conquered. It simply is, vast beyond reason, ancient beyond imagination, beautiful beyond description, and we improbable creatures on our 1-inch marble orbiting a 9-foot star in an ocean of darkness, we have the audacity to measure it, to model it, to dream of crossing it. Consider again where you stand in this journey. You have walked from a 9-foot sun past the 1-inch Earth, past the 1/2-inch Jupiter, past the 1/4-inch Neptune, out to the edge of the Kuiper Belt 7.5 miles away. Behind you lies everything humanity has ever touched. The planets we have orbited, the moons we have landed upon, the asteroids we have photographed, the comets we have sampled. Before you lies a journey of 49,000 miles to reach the nearest star, and beyond that star lie billions more, and beyond those billions lies the edge of the observable universe, receding at the speed of light into an infinity we cannot perceive. The scale is crushing, but perhaps it need not be only crushing. Perhaps there is something liberating in confronting the true size of our cosmic neighbourhood, in understanding our actual position in the hierarchy of structures that comprise reality. We are small. We have always been small. Our planet is small, our star is small, our galaxy is small against the canvas of the observable universe. But we are the part of the universe that has become aware of itself. We are the matter that has learned to measure and model and imagine. We are the brief flicker of consciousness that has looked outward from a 1-inch marble and mapped, however imperfectly, the vastness that surrounds us. The distance from Earth to Alpha Centauri seems insurmountable today. Perhaps it will remain insurmountable forever. Perhaps the stars are truly unreachable, cosmic scenery to be admired but never visited. Or perhaps our descendants will find ways we cannot imagine, will develop technologies we cannot predict, will cross the void in spans of time that seem reasonable to them, even if they seem miraculous to us. We cannot know. We can only measure and dream, and continue. The Voyager 1 spacecraft carries a golden record containing sounds and images from Earth, a message in a bottle thrown into an infinite ocean. That record will eventually pass through interstellar space, will drift for millions of years in the darkness between stars, will perhaps someday, in a probability indistinguishable from zero, be found by something capable of interpreting its contents. The gesture is absurd, the odds are infinitesimal, the distances are impossible. And yet we sent it anyway, because we are the species that reaches, that hopes, that refuses to be defined entirely by our limitations. In our model, Voyager 1's golden record is a speck smaller than a grain of pollen, attached to a spacecraft smaller than a mote of dust, travelling at a pace so slow that it will take 73,000 years to reach the nearest beach ball star. Against the 49,000 miles of empty model space it must cross, against the 2,500 miles of the Oort cloud it must transit first, against the 4,500 miles of pure interstellar void that follows, this tiny speck is less than insignificant. It is imperceptible. It is nothing. And yet it carries with it everything we are. Our music and our mathematics, our greetings and our geology, our heartbeats and our hopes. A fragment of human civilization, frozen in time, drifting through an abyss we have only begun to comprehend. The darkness between stars is vast beyond measure, but it is not empty of meaning. We have filled it, however slightly, with ourselves. The journey we have taken together across this scaled model of our cosmic neighbourhood has revealed something profound about the nature of space itself. We began with a marble, a simple blue sphere 1 inch in diameter, held between thumb and forefinger. We placed a peppercorn moon 10 feet away, a 9-foot sun at a distance of 440 yards, the outer planets miles from our starting point, and the nearest star on a beach 49,000 miles distant. Each step of this journey has forced us to confront the same uncomfortable truth. Space is not merely large. Space is large beyond the capacity of human intuition to grasp without assistance. But now, having walked this mental landscape from the warmth of our scaled sun to the frozen darkness of interstellar space, having traced the path that Voyager 1 will travel for the next 73,000 years, having measured the impossible gulf between our 1-inch Earth and the nearest beach ball star, we must ask ourselves what this journey has meant. What have we gained by confronting the true scale of distances that separate us from everything beyond our tiny world? The answer, perhaps unexpectedly, is not despair. Consider what it means that you can hold this model in your imagination at all. A marble, a peppercorn, a basketball, a beach ball on a distant shore. These are objects you have touched, distances you have walked, scales you can genuinely comprehend. The actual numbers: 93 million miles, 4.24 light years, 25 trillion miles. These figures slide off the surface of human cognition like water off polished stone. They are too large to feel. But a 9-foot ball of fire 440 yards away, a 1-inch marble orbiting that fire with a peppercorn companion 10 feet distant, a beach ball resting on a beach 49,000 miles from where you stand. This you can hold. This you can see. The very fact that we can construct such models, that we can translate the incomprehensible into the tangible, reveals something essential about human consciousness. We are not merely observers of the universe. We are interpreters of the universe. We take the raw data of existence, the photons striking our telescopes, the gravitational perturbations affecting our spacecraft, the spectral signatures embedded in starlight, and we transform that data into understanding. We build pictures in our minds. We create metaphors that let us grasp what our senses alone could never perceive. This capacity for abstraction, for modelling, for imaginative reconstruction of reality at scales beyond direct experience, is perhaps the most remarkable feature of human consciousness. No other species on Earth can do what you have just done. Hold in your imagination a model of the solar system and its nearest stellar neighbour, scaled to sizes you can touch, distances you can walk, relationships you can feel. This is not merely intelligence. This is something stranger, something more powerful. This is the universe developing the capacity to represent itself to itself. And yet, having constructed this model, having walked its distances and measured its voids, we must now confront what the model reveals about our future as a species that dreams of the stars. The 49,000 miles separating our scaled Earth from the nearest scaled star represents a journey of such duration that no technology currently conceivable can complete it within a human lifetime, at any reasonable fraction of light speed. Even travelling at 1/10 the speed of light, a velocity so extreme that no propulsion system yet designed can achieve it, the journey to Alpha Centauri would require 43 years. A child born at launch would arrive in middle age, having spent their entire conscious existence in transit through absolute darkness, watching the sun shrink from a brilliant point to one star among trillions, watching Alpha Centauri grow from a distant glimmer to a resolving system of 3 stellar bodies. At more achievable velocities, perhaps 1% of light speed, roughly 1/1960 miles per second, still faster than any spacecraft humanity has ever built, by a factor of more than 30, the journey extends to 430 years. 14 generations would live and die aboard the vessel. The passengers who arrived would share no living memory with those who launched. The civilization that sent them might no longer exist. The language they spoke at departure might have evolved beyond mutual comprehension with the language of their descendants. They would arrive as strangers from a forgotten past, carrying genetic and cultural information from a world that their arrival era Earth might scarcely remember. These are not engineering problems. These are existential problems. The distances revealed by our scaled model do not merely challenge our technology. They challenge our conception of what a human life is, what human civilization means, what it would mean to truly become an interstellar species. And this is where the crushing weight of cosmic distance begins to transform into something else entirely. Because the question is not whether the stars are far away. The question is what kind of species we choose to be in the face of that distance. We could accept our confinement. We could acknowledge that the solar system is vast enough for 1,000 generations of human expansion, that the resources of the asteroid belt and the moons of the outer planets could sustain human civilization for millions of years without ever requiring us to cross the interstellar void. We could build a civilization of profound depth rather than cosmic breadth, exploring every corner of our sun's domain while leaving the stars to shine untouched above us. This would not be failure. The solar system, as our model has shown, is itself enormous. The 7.5 miles from our scaled sun to the edge of the Kuiper belt represents trillions of miles of real space, thousands of known objects, millions of potential habitats for future human settlement. A civilization that fully developed the solar system would be unrecognizably advanced compared to our current state. They would command resources we cannot imagine, deploy technologies we cannot predict, achieve feats of engineering that would seem miraculous to our contemporary eyes. And yet we are the species that sent Voyager. We are the species that looked at a 49,000-mile void in our model, a 25 trillion mile abyss in reality, and attached to a spacecraft the size of a small car, a golden record containing the sounds of Earth, the mathematics of our civilization, the greetings of our peoples, and a map showing the location of our sun relative to nearby pulsars. We are the species that threw a message in a bottle into an infinite ocean, knowing that the odds of that message ever being found are indistinguishable from zero, and threw it anyway. This is not rational behaviour, measured by the cold calculus of probability and resource allocation. This is something else. This is hope refined into action. This is the refusal to be entirely defined by our limitations. This is the peculiar human insistence that what we cannot yet achieve, we might someday achieve, and what we might someday achieve, we must therefore strive toward. The distances are real. The challenges are immense. The probability that humanity will ever send living beings to another star remains, as of this moment, essentially unknown. Perhaps high, perhaps vanishingly low, perhaps dependent on variables we cannot yet identify. But the act of measuring those distances, of confronting them honestly, of building models that let us truly feel the scale of the void we hope to cross, this act is itself a form of preparation. You cannot overcome what you cannot comprehend. And now, having walked this journey from marble to beach ball, from sun to star, you comprehend something that most humans throughout history could never have imagined. You know where we are. We are on a 1-inch marble orbiting a 9-foot sphere of fire 440 yards away. Our nearest planetary neighbour inward is a marble 2/3 of an inch across, 170 yards from the sun. Our nearest neighbour outward is a rusty marble slightly larger than Earth, 1/2 mile from the sun at its closest approach. Our largest companion is a basketball named Jupiter, orbiting 1.5 miles out. Our most distant known planets, the ice giants Uranus and Neptune, circle 6 and 7 miles from the sun respectively. The edge of the Kuiper belt, the ring of frozen debris where Pluto makes its home, lies 7.5 miles out. The Oort cloud, that vast spherical swarm of cometary bodies marking the true gravitational boundary of our sun's domain, extends nearly 2,500 miles in every direction. And beyond that boundary, after crossing another 4,600 miles of pure interstellar void, we reach Alpha Centauri, a beach ball and a slightly smaller companion, orbiting each other at a distance equivalent to standing in New York, while your dance partner stands in Chicago, with a marble-sized red dwarf circling both of them from much farther out. That is our cosmic neighbourhood. That is the scale of distances that separates us from the nearest star. And that nearest star is merely the closest of 100 billion stars in our galaxy, which is itself merely one of 200 billion galaxies in the observable universe. The numbers, as always, resist comprehension. But the model you now carry in your imagination, makes the essential truth tangible. We are isolated on our small world by distances of such magnitude that even light, the fastest thing in the universe, requires years to bridge them. We are separated from the nearest port by an ocean so vast that no ship we have yet built can cross it. We are, in a very real sense, stranded, and yet we are not without hope, because the same species that built the telescopes capable of measuring these distances is also the species that split the atom, decoded the genome, and landed 12 human beings on a moon 238,000 miles away, using computers less powerful than the phone in your pocket. The same civilization that mapped the cosmic microwave background radiation left over from the Big Bang is also the civilization that went from the first powered flight to orbital spaceflight in 66 years. The same creatures who once believed the Sun orbited the Earth now send robotic emissaries to photograph the moons of Saturn and taste the atmospheres of Jupiter. We are capable of astonishing things when we choose to reach. The question facing our civilization is not whether the stars are distant. They are distant. We have measured that distance with extraordinary precision. The question is whether we possess, as a species, the patience, the wisdom, the institutional continuity, and the sheer stubborn determination to bridge that distance across timescales that make individual human lives seem like mayfly flickers against the slow turning of cosmic time. Perhaps we do not. Perhaps the challenges of interstellar travel will prove not merely difficult but genuinely impossible. Not for reasons of physics, which as far as we know permits such journeys, but for reasons of biology, psychology, sociology, or economics. Perhaps the void is too vast, the journey too long, the investment too enormous, the payoff too uncertain. Perhaps the stars are destined to remain what they have been throughout human history, lights in the sky, beautiful and unreachable, inspiring poetry and navigation but never human footprints. But perhaps, and this perhaps is the one we must cling to if we are to remain the species that reaches, perhaps we will find a way. Perhaps our descendants, equipped with technologies we cannot imagine, sustained by resources we cannot fathom, driven by motivations we cannot predict, will solve the unsolvable problems. Perhaps they will build vessels capable of surviving centuries of transit. Perhaps they will develop propulsion systems that push spacecraft to significant fractions of light speed. Perhaps they will find ways to sleep away the decades, or to extend human lifespans, or to transmit human consciousness across the void in forms we cannot currently conceive. We do not know. We cannot know. The future is not yet written, and the story of humanity's relationship with the stars has only barely begun. What we can know is this: the distances are real, and they are vast, and they must be confronted honestly before they can be confronted at all. The scaled model we have constructed together, the marble Earth, the peppercorn moon, the 9-foot sun, the beach ball Alpha Centauri 49,000 miles away, this model is not merely a thought experiment. It is a tool for understanding. It is a lens through which the incomprehensible becomes graspable, through which the abstract becomes physical, through which the crushing scale of cosmic distance transforms from a number on a page into a felt reality. And felt realities are the ones that move us to action. The child who holds a marble and imagines it as Earth understands something profound about our planet's fragility in a way that no lecture could convey. The student who walks 440 yards from a 9-foot sun model to a 1-inch Earth model understands something essential about our position in the solar system that no textbook could teach. The dreamer who imagines a beach ball resting on a shore 49,000 miles distant, representing the nearest star, understands something crucial about the scale of interstellar travel that no equation could communicate. This is the power of physical models. This is the power of imagination grounded in tangible scale. This is what we have built together across this journey. Not just knowledge of distances, but felt understanding of what those distances mean. And now, standing at the end of this journey, looking back across the model we have constructed, the tiny moon orbiting its tiny Earth, the inner planets huddled close to their parent star, the outer planets scattered across miles of empty space, the Kuiper belt marking the edge of familiar territory, the Oort cloud stretching thousands of miles in every direction, and finally the nearest star glimmering on a beach impossibly far away, we can see our situation clearly. We are small. We are isolated. We are surrounded by distances that dwarf everything we have ever built or travelled or imagined. But we are also awake. We are conscious. We are the universe looking back at itself with eyes capable of wonder and minds capable of measurement. We have taken light years and compressed them into miles. We have taken the unfathomable and made it comprehensible. We have confronted the void and found, within ourselves, the capacity to map it. The darkness between stars is vast beyond measure. It separates us from Alpha Centauri by 49,000 model miles, from the centre of our galaxy by a distance that would require our model to expand to the orbit of Jupiter around the actual Sun, from the nearest major galaxy by a distance our model could never contain. The cosmos is arranged on scales that make human civilization seem not merely small, but infinitesimal. A brief flicker of organised matter in an ocean of darkness and time, and yet that brief flicker has produced something remarkable. It has produced beings capable of understanding their own smallness. It has produced minds that can hold the entire observable universe in a single mental model, that can trace the evolution of matter from the Big Bang to the present, that can predict the behaviour of stars not yet born and calculate the positions of planets not yet discovered. It has produced Voyager 1, still falling outward after more than 4 decades, carrying the sounds and images of Earth into the interstellar medium. It has produced you, standing here at the end of this journey, holding in your imagination a marble that is Earth, and a beach ball that is Alpha Centauri and the terrible, beautiful gulf between them. The scaled model we have built reveals the truth about our cosmic position. We are isolated. We are tiny. We are surrounded by distances that seem designed to humble us. But the model also reveals something else. We can comprehend these distances. We can measure them. We can hold them in our minds and manipulate them and build representations that make the ungraspable graspable. This capacity, this peculiarly human gift for abstraction and modelling, is not nothing. It is perhaps everything. Because before you can cross an ocean, you must first know how wide it is. Before you can climb a mountain, you must first see its summit. Before you can bridge the void between stars, you must first understand exactly how vast that void truly is. Now you understand. You know that when you look up at Alpha Centauri in the night sky, you are seeing light that left those stars 424 years ago, light that has travelled 25 trillion miles to reach your eyes, light that in our model would have begun its journey on a beach 49,000 miles away. You know that the New Horizons spacecraft, the fastest object humanity has ever sent toward the stars, would require roughly 78,000 years to reach that beach, travelling at 36,000 miles per hour without rest or pause. You know that Voyager 1, humanity's most distant ambassador, will take 73,000 years to reach the vicinity of another star, not Alpha Centauri, but a red dwarf in the constellation Camelopardalis, and will not arrive there until approximately the year 75,000 CE. These are crushing numbers. They are numbers designed, it seems, to break the human spirit, to force us to accept our limitations, to abandon our dreams of reaching beyond the tiny marble we call home. But the numbers are not the whole story. The whole story includes the fact that a century ago we had not yet achieved powered flight. 2 centuries ago we had not yet harnessed electricity. 3 centuries ago we believed the sun might be a few million miles away rather than 93 million. Our understanding of the cosmos has transformed utterly within living memory, and there is no reason to believe that transformation has ended. The whole story includes the fact that we are already working on technologies, light sails, antimatter propulsion, nuclear pulse drives, that could reduce interstellar travel times from millennia to centuries or even decades. None of these technologies are ready today. Some may never be realized. But their theoretical existence proves that physics does not forbid interstellar travel, only renders it extraordinarily difficult. The whole story includes the fact that we are a species that has consistently exceeded our own expectations, that has achieved feats our ancestors would have declared impossible, that has reached the moon with chemical rockets and vacuum tubes and slide rules and returned safely to Earth. The distances are real. But so is human ingenuity. So is human determination. So is the strange, inexplicable drive that compels us to reach beyond our grasp, to send golden records into infinite darkness, to point telescopes at distant galaxies, to build models of the cosmos that let us hold the universe in our imagination. The marble Earth rests in the darkness, orbiting its 9-foot sun, circled by its peppercorn moon. 10 feet separate the moon from the Earth. 440 yards separate the Earth from the sun. Miles separate the outer planets from the inner ones. Thousands of miles mark the boundary of our sun's gravitational domain, and 49,000 miles of pure, empty model space separate us from the nearest star. This is our situation. This is where we are. This is the scale of the challenge that faces any species that hopes to become truly interstellar. And yet we are not without resources. We have minds capable of understanding. We have hands capable of building. We have institutions capable of preserving knowledge across generations. We have the example of our own past achievements to prove that the impossible can become possible. We have time, perhaps not much time on a cosmic scale, but time enough to dream, to plan, to prepare, to begin. The stars are waiting. They have been waiting for 4.6 billion years since our solar system formed, waiting for 200,000 years since anatomically modern humans emerged, waiting for 60 years since we first escaped the gravity well of our 1-inch marble and touched the surface of our peppercorn moon. They can wait a little longer, and when we are ready, if we are ever ready, we will find them still there, still shining, still separated from us by distances that once seemed impossible, but that we will have learned, somehow, to cross. The void is vast. The darkness is deep. The journey is longer than anything humanity has ever attempted. But we are the species that reaches. We are the species that measures and dreams and refuses to be defined entirely by our limitations. We are the improbable consciousness that has arisen on a 1-inch marble, orbiting a 9-foot star, gazing outward at a beach ball 49,000 miles away, and daring to imagine the journey. The universe is under no obligation to make sense to us, or to be crossable by us, or to welcome our presence among its scattered stars, but we are under no obligation to stop trying. This is what the scaled model reveals in the end. Not merely the vastness of space, though that vastness is real and must be respected, but also the remarkable capacity of human consciousness to hold that vastness, to measure it, to model it, to transform the incomprehensible into the merely difficult. We know where we are now. We know the scale of the challenge. We know that 49,000 miles of model space, 25 trillion miles of real space, separate us from the nearest star. And knowing this, truly knowing it, feeling it in our bones and our imaginations rather than merely reading it in a textbook, we can begin to ask the real question, not whether the stars are far, but how we might someday, impossibly, improbably, reach them anyway. The marble earth hangs in darkness, blue and small and precious. The beach ball star glimmers on a distant shore, and between them stretches the void, vast, silent, patient, waiting for the species that reaches to find its way across.